a few words, a few introductory words to this event. For those who do not know me, I am Matteo Frangi, the head of the department. And I would like to welcome you to this seminar of the Scientific Committee. The topic of today's seminar is building the energy transition through the technologies of environmental and civil engineering. It was the topic of the scientific project that we produced as the department for the Excellence Program of the Ministry of Education and University. As usual, the seminar will be split in two phases. The first phase, in the first phase, we will have two seminars from two distinguished external speakers, whom I would like to thank warmly for accepting our invitation. Thank you, Karen. Thank you, Andrea. And in the second phase, on the contrary, we will have 6 presentations delivered by 6 young researchers from our department on the topic of the seminar, of course. The aim of this seminar is, of course, to stimulate a lively and interesting scientific discussion on an important topic. And by doing so, also to stimulate and favor cohesion in our department, which is a relatively large one with 300 people, 120 staff, and 180 PhD and postdocs. It is, moreover, a relatively young department. We are celebrating 10 years right now. And this year, for the first time, we are sharing one common location, physical location, while we were split in different buildings until December. Actually, we are still split, but only into 2.5 buildings. As a matter of fact, we will have the inauguration on the 11th of September this year. So we want to favor cohesion and to disseminate all the different skills and expertises which are typical of all of us. It's very difficult, even for me, to know all of them. So this is a very good occasion for doing that. Let me also recall that associated to the 6 presentations by the young researchers, there is also a prize, the prize of the Scientific Committee, which is meant to help young researchers in the preliminary steps of the academic career. So it is really important to us. And okay, so I will give the floor to, if I'm right, Max, who will be introducing our first speaker, Karen Scrivener. So please, Max.
So good morning, everyone. I'm very pleased to welcome here our first speaker, Karen Scrivener. Karen, I don't want to make a long list about her achievement and her career, just a very, very quick presentation. Karen graduated Cambridge University and then got a PhD from Imperial College, and where I also start working as a first postdoc, then lecturer. And what is interesting in her career is that then she moved to industry and started working for Lafarge for many years. And then in 2001, she came back to university at EPFL, where she is now head of his laboratory of material science. And I don't want to list all her achievements and her prizes, but I just want to mention his role in promoting sustainable materials like cement and concrete, and in particular in his their possibility to reduce the CO2 emission. So thanks, Karen, for being here. And today she will present a talk titled Sustainability of Cement and Concrete Getting to Zero. Please, Karen, you can start.
So thank you. So does that work? You see the screen okay?
Yes, perfectly.
Okay. So thank you for inviting me to speak at this seminar, and sorry not to be with you in person. So yeah, this presentation has various titles, but you know, really we're talking all the time about cement and concrete, what they contribute to CO2 and how we can do something about it. Now, I like to start with this slide, that this is some projections of what can happen to the Earth climate under various scenarios. And why I like to show this is because there's two messages here. First of all, many young people say to me, well, it's too late. No, it's never too late to make things less bad. You see this line at the top? This is the scenario if we do nothing, we just carry on like we are today. It's predicting a rise to 7 degrees at the end of the century. And we know this would be completely catastrophic. And everything we can do in these new scenarios will bring this down. And of course, the best scenario is the one at the bottom. And this is the scenario where we can reduce to 0 by 2050 or soon after. So anything we can do now will still make things less bad, but these things we can implement fastest will be the most important, because, you know, saving CO2 today is really the essence. It's no good having some miracle solution that maybe comes along in 50 years. Then it's really getting late. So this is, you know, why we need to move fast. This was a summary of the latest document on this from the UN Secretary General, that, you know, we really need developed countries to commit to reducing to net zero by 2040, even emerging economies by 2050. And the first thing to do is stop burning coal. I won't go through all of this. But all of these sectors, you know, it's not for, we don't just have to work on cement, we have to work on all of these sectors. So I think your seminar today is very interesting by looking at these different sectors. Now, a lot of emissions are coming from buildings. Focus in the past has been mainly on the operational energy, that's to say energy efficiency, heating, cooling, things like that. We have good solutions there now. And I think moving forward, we need to focus on this so-called gray emissions, these embodied CO2, which are also the things that come very early on in the life of a building. The other aspect I really want to introduce here is, you know, the fact that we can't just say we stop building. Yes, in these developed countries, Switzerland, Italy, if we stop building now, we could probably make do. But this is not the situation in many parts of the world. We still have more than 1 billion people today living in slum conditions. And, you know, apart from the sort of moral obligation, it's also in our own self-interest, because if these people have such poor living conditions, well, it's not surprising they want to migrate to Europe, taking huge risks with their lives and drowning in the Mediterranean. So, you know, we really have to work on the whole world. And we also have to think about the whole world, because, of course, CO2 knows no boundaries. You know, living in a small country like Switzerland, we could reduce our emissions to 0, but this would have really very small impact. We have to work on all parts of the world. Now, turning to cement, of course, a lot of people say, you know, and quite rightly, that cement is accounting for something like 7 to 8% of world CO2 emissions. This is a large number, but it's not coming from the fact that concrete, which is the end product, is a high CO2 material. You can see in this graph at the top right that, in fact, the emissions, intrinsic emissions per kilo of products based on cement are in this bottom right corner. This to say they have much lower CO2 emissions per kilogram than almost any other material. And it's really then this huge emissions is coming from the very large amounts of materials we produce, something like 30 billion tons of materials based on cement, that's to say concrete and mortars, are produced each year. And this also means that there's no practical way to replace them. So even something like timber, which can be produced in a sustainable manner, the amounts that can be produced are really very, very small compared to this demand. Today, timber is accounting for something like 5 to 10% of construction materials, and that's not sustainable. We're cutting down more trees than we're planting. It's been estimated that if we wanted to replace just 1/4 of cementitious materials with timber, we would have to plant new forest 1.5 times the size of India. And of course, that would be a jolly good thing to do. But even if we did it tomorrow, we still have to wait something like 30 years for it to produce timber. Now, people say to me, well, you know, a kilogram of concrete is not the same as a kilogram of wood. And that's again true. But then, you know, when we look at the building level, there was this study done in Europe last year, which compared different types of building in terms of the kilograms of CO2 per square meter. And here are the different building types they managed to look at. I think the main thing is there's not much difference on average between these different types of material. But what is very striking is, particularly if we look at this column here, which is the massive concrete, in fact, the lowest CO2 per square meter building in the study was in concrete, but also the highest one. And clearly, if we can get rid of all these high buildings up here and make them all down here, we have a much bigger impact than the very marginal gains we can have by building more buildings in wood, for example. And then coming back to the world situation, you know, we can look at cement and we can see this is really representative of construction as a whole because it's so dominant. And you see this tremendous changes that have taken place in the last 50 odd years. When I was born over here, almost all cement was used in the global north. And then from notably from 1990, we had the huge development in China, which now accounts for about half of cement production. But when we look at the projections to 2050, we see there's going to be another massive shift. China is going to go down, and that's not really surprising because the average consumption per person in China is 3 times the world average, and it's going to shift to these other developing regions, India, Latin America, Southeast Asia, and very importantly, Africa. So by 2050, it's really projected that these other developing regions will account for more than half of cement consumption. So we really have to engage with these companies. We have to make partnerships with them to find the best ways to construct the constructions that are needed with the minimum CO2 emissions. This can also be translated into, you know, how much of a country's emissions are actually coming from cement and concrete. We have this world average figure of 7 to 8%. But when we break this down on a per country basis, we see in developed countries, notably the United States, the emissions are only 1.5% coming from cement, where in European Union, a little bit higher, but still only about 3%. Whereas in developing regions, Vietnam, Nigeria, we have around 20% of their country's emissions coming from cement and concrete. So this again emphasizes where we need to focus our efforts. Now, the good news is that it's really clear that we can make reductions. There's no miracle solutions, as I will explain, but if we really work through the whole value chain, if we work at all the different steps, we can make very substantial reductions, even of the order of 80% or more. So the different steps in the process of cement, first we make what's called clinker, and we have to make this efficiently. Generally today the plants are quite efficient, but then we have to reduce the clinker in the cement, and we can do that by introducing substitute materials, which I'll talk more about. But then we have to carry that through to the concrete by minimizing the cement in the concrete, and that can often be as simple as using admixtures. We also have to look at good design, reducing concrete in buildings, and then, really considering, do we need to demolish buildings? Can we reuse them? And if we do demolish them, can we recycle everything? So this is the main message. There are big reductions to be made, but only if we work at all steps of the chain. And this has been recognized in many roadmaps. This roadmap is coming from the Global Cement and Concrete Association. You see the steps I talk about: efficiency in design, efficiency in concrete production. These are the same kind of things. What is really striking, though, in this roadmap is the large amount of reduction that is still projected to have to come from carbon capture and utilization or storage. Now, as we see in this graph over here, if we can increase even slightly this first step in the process, we can really reduce this need for carbon capture and storage. And why do we need to reduce this need? We need to reduce it because this is the really expensive part of things. All these other steps, efficiency in design, efficiency in concrete, savings in cement and binders, can in fact be implemented at near neutral or even negative cost. And, this is really what we can do fast. At the end of the day, we're still going to end up with something left over, and that will have to be dealt with by carbon capture and storage. But in terms of cement usage, that will be quite expensive. That will put up the price of cement by 2 to 3 times. And the reason for that is, first of all, you have to have the capture. And in the long term, costs for capturing a ton of CO2 by various technologies are looking to be around 40 to 50 euros per ton. But then we have the problem of permanent storage, because, this here on the right is the pipe network that was deemed to be necessary if we're going to get all that captured CO2 to storage sites, which in Europe are mainly, we're talking about disused oil wells, but increasingly there's going to be more deep storage sites opening up. Now, coming back to the process of making cement and looking at what we can do, it's very important to keep our feet on the ground, to be realistic. So this is a cement plant. Many of you will perhaps have seen these. They're actually really quite efficient today. And it's estimated there's probably not very large savings that can be made here. And moreover, these cement plants can now use very wide range of fuels. So we can almost totally stop using fossil fuels in this process. And only 40% of the CO2 emissions are in fact coming from the fuel part of this production. The largest part, about 60%, is coming from this simple chemical equation here, where we have limestone, which is calcium carbonate, and limestone is about 80% of the raw material to produce cement. And during the first stage of the process, this decomposes to calcium oxide and CO2. So then people say, well, why don't we make cement with a different chemistry? Well, perhaps it would be nice, but unfortunately, it's not possible because of the composition of planet Earth. This shows the composition of the Earth's crust, and we have just 8 elements which make up more than 98% of the Earth's crust. So we have oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. And clearly we can't use anything in that remaining 2% because there's not enough of it. We already have, in lots of technologies, we have a lot of bottlenecks. For example, people talk about hydrogen as a green fuel, but the bottleneck there is iridium production. We need to produce the electrolyzers. We only produce about 4 tons of iridium a year. And on that basis, it would take 100 years to produce enough electrolyzers even to replace the hydrogen we're already producing today. And then we need to consider, well, how does cement work? So amongst those 8 elements, what are the elements that work? Well, very simplistically, we take this grey powder, we mix it with water, and to start, the grains are just floating about in water, but then they dissolve like sugar dissolves in your coffee. And then we have something else going on, which is a very important part of the process, that the ions get together to form other compounds, which are called hydrates, and these precipitate and they hold the whole thing together. They give the strength and the durability. So when we go back to the composition of the earth, and we look at the oxides of the alkalis, sodium, potassium, these are just too soluble. So they dissolve no problem, but they don't form hydrates. On the other hand, the oxides of iron and magnesium, we have the opposite problem of too low solubility. And this just leaves us with 3 oxides. So this is really quite incredible. We can go from analysis of the whole Earth's crust, and we can see that to make cements in these very large quantities, we have to use compounds based on just 3 oxides. Now, this system of calcium, silica, and alumina has been studied for more than 100 years. We know all the phases that form in this system. And basically, we have just 2 areas. We have this area here, which we call Portland cement, which is basically calcium silicates. And we have also this area here, where we have calcium aluminate cements, calcium sulfur aluminate cements. And this area has achieved a lot of attention because you see it's further from this calcium oxide corner, and that means there's less calcium oxide, and therefore we need less limestone, so less CO2. Sounds great, but unfortunately, to get down to this corner, we need to have sources of minerals which contain much more alumina compared to silica. And these are not abundant. Basically, we're talking about things like bauxite, which is very localized. And of course, we use bauxite to produce aluminium, which makes it expensive. But even if we took all the current bauxite production, we didn't produce any aluminium, we would still only be able to replace something like 10 to 15% of this demand. So basically, these are going to be niche products, which are not going to lead to large-scale CO2 reduction. And despite the media interest they attract, I haven't got time to go through them all in detail, but a lot of hype solutions like getting alkali activated materials, cement from algae, etc., they're either impractical, very costly, and sometimes we're talking about costs more than 100 times of the product we have today. We don't have the resources to make them scalable, like I've just explained to you about calcium sulfur aluminate cements, or they're way too along in the future. So, we really have to focus on what we can do now. And we have to accept that Portland-based cements will continue to dominate, but what we call blended cements, so that's replacing as much as possible of the clinker with other materials, is the most realistic option to reduce CO2. We can do it fast, and we can also extend resources. So in a nutshell, this is like 50, 100 years ago, cement would have been clinker and gypsum ground up to produce cement. Nowadays, most cements in the world contain what we call supplementary cementitious materials, and these can be things like limestone, which comes from the same quarry to produce cement. This can be fly ash, which comes from burning coal. Of course, coal, as I said earlier, is the #1 problem in climate change. So how long is fly ash going to be around? Slag comes from producing iron in blast furnaces, and again, this is a very CO2 intensive process. Then we have calcined clays, which is what I'm going to talk more about because this is the real potential game changer, which can vastly increase the amount of substitution materials we have. So even today, these classic SEMs, the slag coming from iron production and fly ash, are only available in quite limited amounts compared to the demand for cement. So slag, for example, is about 8%, and 95% of that slag is already used. So if you specify high slag in your project, you're just taking it away from another project, and globally we don't have any net reduction, more reduction in CO2. So this is where limestone is super abundant, but you can't use more than about 10-15% before it just becomes simply a diluent. This is where clays come in, because when you calcine them, they can be very reactive materials. And this is what led to our project, which is called LC3. We realized the importance of calcined clay, but then we found out that using a combination of calcined clay together with limestone allows very high levels of substitution. So this is the LC3 project, stands for limestone calcined clay, was supported for a long time by the Swiss government, and now we're supported by Climate Works Foundation from North America. So LC3 can reduce CO2 because we replace 50%, or we can even replace more than 50% of the CO2 emitting clinker with a combination of limestone, which has no CO2 emissions when you don't heat it up, and calcined clay, which has some emissions from the calcination process, but these are much, much lower than clinker. And overall, you can get reductions at this 50% substitution level of about 40%. Now, what's even more interesting is that when we look at this 50% substitution level, we can achieve the same strength in as little as 7 days. So, you can have better performance with 40% less CO2. Now, the kind of clays we need clays with this so-called one-to-one structure, this mineral kaolinite. And this is sort of one layer of silica and one layer of alumina. When this is heated up, this becomes disrupted, and both the silica and alumina are available to react. So silica reacts in the classic pozzolanic reaction, and alumina is the part that reacts with the limestone to give these space-filling hydrates, mono and hemicarboaluminate. We can see on the X-ray diffraction here, which contribute to the properties. If we compare the calcined clay blends to the blends with fly ash and slag, we can see that at long ages, they all have approximately equivalent performance. But the interesting thing about the calcined clay blends is that they catch up in strength much quicker than either fly ash or slag. And in fact, if we work on the grinding, we can even get similar strengths at only 1 day. We have issues with standardization. I'm not going to go into those in detail, but the main message is that we have very complex standards today. And we have the acceptance now of LC3 blends down to 50% clinker, but in the long term, we need to go further and we need to develop performance standards. I said that we needed this kaolin component, but we don't need a high purity. So some of you may have heard of the product metakaolin, which is very expensive. It's used in the paper industry, for example, and it can be 3 or 4 times more expensive than cement. And there aren't that many deposits with very high purity. But what we need is only a limited amount of kaolinite. So we don't, these can often be wastes. Now, these kaolinitic type soils are very, very abundant worldwide. Anywhere in either of these maps you see this kind of yellowy orange color, we will have kaolinitic clays. And you can see they're particularly abundant in those developing parts of the world where the demand for the cement moving forward is going to be highest. And this is what's important, because these are the places there's really no slag and fly ash today. So if they're going to use these substituted cements, they have to go to something like calcined clay. And we can measure the content of kaolinite quite easily by looking at thermogravimetric decomposition. We've done this now for more than 100 clays around the world, and we see this correlation with the kaolinite content. But as I said, the red lines are the reference strength of the pure Portland cement. And you see, to match this reference strength, you only need something like 40% kaolinite content. Now, this is the reference strength of the pure Portland cement. If you want to match the properties, say, of a fly ash cement, then even 30% kaolin may work quite well. And the calcination of the clay can be achieved with existing technologies. You can even do it in a cement kiln with hardly any change. So this means it's, accessible today. And the emissions can be as little as 1/10 of those of clinker, even with using a fuel-driven process. And because the temperature of calcination is quite a bit lower, then in the near future, I think we're going to see a lot of electrification of this process. So this was the first house we built in India. We now have pictures in mainstream construction by the first movers in this area. So this is one of the first plants built in Ivory Coast by Simpor. What was also nice to demonstrate in this plant was that we can control the color of the clay, because in the untreated states, clays tend to be red due to iron oxide present, but we have quite simple commercial technologies for converting that red color into gray if people don't want to have red cements. Key advantages, well, chloride resistance and alkali silica resistance to alkali silica reaction are the top two, and chloride resistance is the #1 cause of durability problems in cement and concrete today. And here we see comparison of the chloride ion penetration, first of all in the reference, which is the black here, which is the pure Portland cement. Then we have mixtures with slag in red here, which are somewhat better. Mixtures with fly ash, which are a bit better still, but the best blends are the ones with the calcined clay. And the diffusion coefficient for the blends with the calcined clay are something like 1/10 of the reference. So the potential is really enormous. This graph here shows how the average level of substitution of clinker around the world has developed in the past decade or so. And you see that basically in the past decades, nothing really has happened. There was a big progress in the 90s in increasing levels of substitution, but since about 2010, really nothing's happened. And the reason for this is the limitation in supply of fly ash and slag. Now, if we remove that limitation, which we can clearly do with calcined clays, we could increase the level of substitution very quickly, because there's no technological obstacle, to something like 40%, which would represent about saving 400 million tons of CO2 per year. So that, for example, is about 10 times the entire emissions of Switzerland, and it's about 1% of overall CO2 emissions from everything. So this is one single technology, can bring about 1% reduction. But if we think about a horizon of 2050, then I think we can increase substitution levels, and we can potentially go to at least double that. So I think here from this one single technology, we have a potential to cut world emissions by 1 or 2%, which considering cement itself is only producing about 7, that's quite an important thing. Financially, in terms of production, more good news, it's generally cheaper than the reference Portland cements. And I'm pleased to say we're now working with all these countries around the world to implement this in practice. These are some of the publicly announced projects that are going on. I think we have something like 9 plants in operation today, but we know that there's going to be at least 30 more on a horizon of the next 2 or 3 years, and hopefully more and more from then on. But coming back, I want to really say that, this is the first thing we can do. It can be done fast and at scale, but it's not the only thing, because we have to then pay attention to the other steps in the process. We have to, for example, look at reducing cement in concrete. And here again, there's just tremendous waste going on. These points here are, data collected from around the world, and it's normalized in terms of the amount of binder, which is proportional to the amount of CO2 per kilogram per meter cubed of concrete, and then per megapascal of the strength, because obviously high strength concretes consume more cement than low strength concretes, but you need to use less of them. And here the message is, well, look at this dispersion. This concrete up here is using four times as much cement as this one down here for exactly the same performance. So this is wasting 75% of the CO2 in that concrete, just totally wasted, totally unnecessary. And this shows you also the huge reductions that can be made by paying attention to these things. And it can be as simple as moving from site mixing, which is generally rather inefficient, to more industrialized processes of ready mix. This has largely occurred in Europe, but still needs to take place in many other parts of the world. What we certainly don't want to do is go to something like 3D printing, which goes in completely the opposite direction. So while you may be able to use less material, the amount of cement in those concretes is very much higher because you can't have large aggregates. So just, concluding there, I think we need to realize that we can make very large reductions. The industry is committed to this. It still needs to be pressurized to do more. We always need to do more, but at least they are making an effort there. And we have to recognize all these different steps of the process. We have to recognize how we can work at the cement level, at the concrete level, and at the structure level. And all of these, generally will lower cost. So, they have a double benefit. You will, at the end of the day, always have a certain amount of CO2 that can only be dealt with by carbon capture and storage. But this will be high cost. And the problem is that the infrastructure is not yet in place. In terms of, the first part of this cement level, calcined clays are the only realistic option for extending the use of SEMs. And the good news is that these can be done fast and at scale. So in really short time scale, we can achieve very large reductions. And most of those reductions depend on getting the different components of the industry to work together. So this is an initiative we've launched through 6 professional societies like the FIB, RILEM, etc., to really try to bring the different parts of the sector together to identify ways we can quickly implement these CO2 savings in practice. And with that, I'd like to thank you and happy to answer questions if you have them.
So thank you very much, Karen, for a very inspiring lecture. Do we have time for a couple of questions? Are there any questions here from the audience? If you want to ask a question, you have to switch on your mic. Oh, I can start with one very general question, which I have. You are proposing a very interesting solution for this very complex problem. How do you think we are far from a real application to large scale of your ideas, and what do you think are the main critical obstacles to the full scale and real scale application, large scale better application of this technology?
Yeah, well, we do already have large scale applications. I kind of was shuffling my presentations around this morning and I forgot to include these very nice pictures from Colombia when you can see LC3 being used in multi-story buildings, in motorway buildings. So it's already there at large scale. There's no obstacle to doing that. I think the reason it takes time is because, all these industries, the main obstacle is people don't want to change. They've been doing things a certain way for a long time and they don't see the need to change. This is starting to change now, which is good news, but it needs to go much further. And, if you consider a cement plant is producing cement 24 hours a day, 7 days a week, something like 320 days a year, they don't have time to do trials or test new things out. So in terms of our project, what we've done, we've set up what we call technical resource centers to do a lot of this trialing for the companies. And as I say, this is starting to bear fruit. We've now got 9 plants going in the world already and another 30 coming online in the next 2 to 3 years. So, technologically, there's no obstacle there anymore. This can all be done. It's just the question of people taking the initiative and just doing it. But fortunately, now that we've managed to get the message across, certainly to the large producers, we've still got more work to do on the small and medium-sized producers.
Thank you very much. Are there any other questions?
Maybe I can ask one question concerning one of the first slides that you have shown, where you were comparing different building technologies in terms of carbon production, and you showed that when you use massive concrete, you can have a huge spread. So the minimum and the maximum, if I remember well. which are the main reasons for this huge spread? Maybe you mentioned some of them during your presentation, I imagine. But
well, I think the main one is people are just not paying attention to it. It's the strategies to reduce the cement content are well known. Basically, the two most important ones are making sure that you have a good gradation of your aggregates, to make sure you have large ones and small ones in the right proportions to minimize the amount of cement you need to fill the gaps. And the second one is to make use of modern admixtures, which allow you to have good workability even at low cement contents. There is an issue in standards. I mean, the European standard has been not helpful, because for years this has imposed limits typically around 300 kilos per cubic meter of concrete, which is, the mistaken idea that this is about durability, because these standards are written in the days before superplasticizers existed. And in those times, then you would need to put in that amount of cement to get a low water cement ratio. But today you don't need to. I'm pleased to say that this is changing. I mean, I think the discussion on the change is just about done. And I know it should be implemented end of this year, beginning of next in Switzerland, and I hope quickly in other countries around Europe. But then, then people have to change their habits. They have to realize they can now go to lower cement contents. And they have to, reformulate their mixes. It's not difficult to do, but it's just each thing, it takes time and effort.
Thank you.
Okay, I think we now have to move to the next speaker, so we take the opportunity to thank Karen again.
Thank you very much, Karen. Yes, okay, and good luck with the rest of your meeting.
So I leave the floor to Francesca to introduce our next speaker.
Okay, thank you. And thank you, Andrea, for coming. Andrea is not a scientist, he's not a researcher, but he will bring us a very important, in my opinion, but I would say according to the triple helix concept, meaning that we need to cooperate research, industries, and institution to get innovation, mostly in this field of the energy transition and the circular economy, where, as Karen said already, we do not have so much time, and we really need to get to efficient solution. So Andrea will bring, well, Andrea, I have to present you. So he's at present a managing director in Italgas. Previously, he had a quite long experience, more than 20 years, in utilities, and mostly water utilities. Water utilities are now faced with a very stringent requirement in terms of energy neutrality, according to the new draft of the Urban Wastewater Directive, meaning that plants serving more than 100,000 population equivalent, which is really a small, medium-sized wastewater treatment plant, should reach the energy neutrality in 2025, which I think it will 25, according to the last draft. Anyhow, it's very short time. Okay, so Andrea, thanks.
Good morning, and thank you, Francesca, and thank you all for this opportunity. I'm not a scientist, so you will not see numbers, but basically something regarding the experience I had in my professional life. I used to work in the water industry as an industrial engineer here from Politecnico of Milan. I started my career in Veolia Group, basically on the design and build side of drinking water treatment plant or wastewater treatment plant. Then I moved to Gruppo Cap, which is a public utility here in Milan, taking care of all almost 200 municipalities all around Milan except Milan, where I was in charge basically of operations at the beginning. It was not romantic. My title was wastewater director. Since 1 year, I moved to the gas industry, which is quite a discussed industry with several challenges, and I'm now in Italgas, so from less than 1 year. And in the middle, you see that during my weekends, I try to collaborate with certain startups, almost focused on environment, as think about, but also on artificial intelligence and automation, because I'm quite curious and I believe there are strong interaction between all these different industries. First of all, think about a manager, or at least somebody who tries to be a good manager. We have to think about the constraints we have in the utilities. Which are the constraints? You will see a lot of constraints, and I will only refer to the most critical ones. Regulatory constraints. Gas, water, energy, and the waste are under tough regulation in Italy, ARERA. Waste since a few years, 1 year, 2 years. Water, 7. Gas and energy, more. But we always have to operate under these constraints, which can be different between different countries. So sometimes you can innovate in a certain country, France, but not in Italy, because there are legislation and regulatory constraints. The second one, of course, technological challenges. Normally, when I always tell to my colleagues, if you can copy from the best countries where regulatory constraints or legislation constraints are not so tough, you can import nice technologies which are used in other countries but not in Italy. I will make an example in a few seconds. Environmental constraints, of course. If you work in a utilities, you have to look at on these constraints. Just to give you an example, Professor Canziani knows, air emission from incineration plants in Italy are really tough compared with Switzerland, Ginevra, 10 times more or less, 10 times less. And we are speaking about Ginevra, Switzerland, not other countries. Economical constraints, easy. Infrastructure limitations. We are dealing with aging infrastructures. We always want to innovate. We always want to be fashion, but we have pipes with more than 50 years of aging. And not everywhere we have money to invest on pipes. So sometimes, also our politicians, I'm a manager, I will speak, they always look forward, but sometimes you have also to look what you are operating. This is very, very important. Resource constraints. In the gas industry, you can imagine, but everywhere you can imagine. Energy was a tough challenge for everybody last year and 2 years ago. But even on other kind of constraints, the deal is strong. And public perception. Crazy, but for example, if you want, and we will have an example, to build a biomethane plant in Italy, you have to fight against the public opinion, which is not always okay with renewable energies. And some others, cybersecurity, political, legal, demographic, and so on. When I arrived in Group CAP, this is quite a strange slide, but when I arrived in Group CAP as a wastewater operation director, I tried to define with my colleagues a master plan towards the circular economy. This is the original slide, which is not easy to be understood, but the idea was, let's try to extract whatever we can from wastewater, because we are not investing enough on what we call circular economy. So we defined an investment plan, almost 250 million, just to give you an example, to maximize the energy extraction, cogeneration, of course, but also district heating, biomethane, and so on, to maximize or at least to try to extract phosphorus or bioplastic. This was research. I worked with several of you on that challenge, to try to maximize the use of reused wastewater and so on. Okay, so this was only the way I tried to share with my colleagues what we wanted to do. There is also something exotic like restoring of ancient irrigation canals. Flooding in Milan, where the story tells us that Leonardo da Vinci a lot of years ago gave us the potential to use all the irrigation channels. Flooding can be minimized by using existing infrastructure, all the existing infrastructure, for example, and so on. I don't want to annoy you on it, but in certain case, we were able to implement these basic technologies. In certain case, we were not able. On the left side, for example, you have something for which I'm crying every day. I was not able to invest on technologies in order to recover heat from sewage, not from the outlet of the wastewater treatment plant where you can do it. But my idea was, at that period, to try to extract heat from the sewage close to big buildings in order to try to use this technology, which is used in France. If you go in Paris, you have at least 10 case studies. In Italy, it was impossible because of cost, because of regulation, and because of permitting issues. Why regulation? In France, for example, they are trying to minimize the extraction of water for heating, for the, how do you call it, the pompe di calore, for heat pumps, because they were pushing too much on the use of groundwater for heat pumps, and the NAP was, facing certain problems in terms of quantity and in terms of quality. So there was a legislation telling if you want to extract water from heat pumps purposes, you have to respect a certain distance between one well and another well. And that's why this technology was able to grow up. I wanted to have some case study, I was not able. On the other side, it's an easy example for today in 2023, but in 2016, the legislation didn't allow to produce biomethane from sludge, from the anaerobic digestion of sewage sludge. Incredible. You could do it from organic waste in Finland, in UK, and in Germany, in France, everywhere it was possible to produce biomethane, not in Italy. In Bresso Niguarda, close to here, Bresso Niguarda was the first wastewater treatment plant in Italy extracting biomethane from sewage. And there was another plant in 2016, huge one, Montello, from organic waste, but only 2 plants in 2016, incredible. And we had to change the legislation. We had to convince politicians and a lot of people, you remember, it was to give us the possibility to extract biomethane. Quite often, and even in that period, we didn't use we didn't reuse wastewater, treated wastewater for irrigation or for other purposes. We started in 2016, and by the end of 2022, we were at 35–40% of the overall production, more or less, but with no direct reuse. Only in 2021 we had the possibility to reuse water for certain park, for the irrigation of certain park, Parco Nord. Water reuse in Italy is easy to be implemented because on a technological point of view, if we don't think about micropollutants for one moment, we are ready to do it, but there is a cost constraint. Agriculture is not keen to pay for water. For them, water is for free. So if you give them water from a wastewater treatment plant, they don't want to pay on one side. On the other side, always the public opinion. There is not only reuse the wastewater, there is also no drinkable water. With the environmental regulation pushing to better performance in terms of the quality of the drinking water, there is a lot of water which in some years could not be drinkable, but can be used for other purposes. That's why, for example, here in Milan, we started the implementation of a network of non-potable wells. Now there are almost, if I'm not wrong, 150, and we use them for gardening purposes, basically. And last, regarding my experience at the beginning in the Gruppo Cap, we were pushing a lot on sludge. The way we, I mean, sorry, it's in Italian, it's a mistake on the left side, but we had to face several, let me say, dramatic moments because of several changes in law. If I'm not wrong, we had at least 10 changes in law in 3-4 years, something like that. And each time, one kind of sludge was okay for agriculture or not okay, and that's why we try to invest in order to maximize the anaerobic digestion of sludge, first of all. I mean, not a lot of years ago, but anaerobic digestion was not so much used in Milan in 2016. The biggest, one of the biggest plant in Italy, which was not operated by us, but by Metropolitana Milanese, which is Nosedo, plant treating half of Milan, had no, I mean, has not anaerobic digestion. Only a few days ago, they received the permit to build anaerobic digester. Just to give you an idea. So we try to maximize the use of anaerobic digester from 0 to 60% of our sludge. We tried, of course, to work on the watering and whatever. And then in that period, we started thinking about the use of sludge as fertilizers. In 2016 was allowed, but with the organic fertilizer regulation of 2021 from the European Commission, if I'm not wrong, 2020. Yeah, but then, okay. It will not be allowed, and so on. The output of all our things was that now we are Gruppo Cap. Sorry, sometimes I feel as I'm. Gruppo Cap is building an fluidized bed incinerator for sewage sludge on one side, closing an existing indifferentiated waste incinerator plant. So we closed that one and we are building a dedicated plant for sludge on one side. And on the other side, we are building, I mean, and they are all already working. We are using the anaerobic digesters, which we previously used for sludge, for organic waste produced by the municipalities, which before used the incineration plant. Huge project. The name is Biopiattaforma. There is a website. If you want more information, I will give you. So we were in 2016. Master plans toward the circular economy, several millions of investment plans, and then the Urban Wastewater Directive. 2022, some of the investment we planned are still okay, some have to be revised. The wastewater directive, the new proposed Urban Wastewater Directive has different challenges. The first one is on the management of the storm water. There was no regulation. I mean, there was a regional regulation in Lombardy regarding the way we had to try to deal with the storm water. And then in 2019, I think, the regional regulation was updated. But in any case, stormwater means only for the suburban area of Milan, almost 1.5 billion euros of investments. just to give you a certain number. And this will increase the concentration of our wastewater at the inlet of the plant, probably. So basically, nice. Nitrogen and phosphorus, they are telling us that they want to decrease the outlet concentration. Okay, possible with the existing technologies, even if expensive. Micropollutants, tough. There are not so many technologies today. We tested with Polytechnic of Milan several ones, but of course, we will have to invest on these technologies on one side, and on the other side, we will have to consume more energy. This is for sure. And I mean, the real challenge is the energy neutrality of the wastewater treatment plant. On one side, it will be impossible on little wastewater treatment plants, as you can imagine. It will be probably possible on the biggest one, but not with these wastewater concentrations, and not if we don't look with the interaction on with other industries. I will explain you in a few moments. So here you have the interactions. Basically, this on the right side you have a document from Utilitalia, which is the association of utilities in Italy. This document was sent to the European Commission, and basically Utilitalia told to the European Commission, we are not ready to satisfy the challenges of the new wastewater directive. We have to push more on research and development, because on a certain side there are no technologies. And this is Utilitalia. On the left side, my opinion, if we look only at the water industry, we won't be able to face this new challenge, but we have to open our view and try to create more interaction with the food industry and with the energy industry. In any case, I'm strongly, it's my strong opinion that we have to start trying to replying a certain case study we had with the university. I will explain you in a few moments of what I call living labs, what Francesca called living labs. So we need industrial partners, and we need universities and the research center to try to come into the plants and to push for pilot plants, for the installation of pilot plants, and for assessing if they work or not on a performance point of view and on an economical point of view. We had a fantastic experience with you. The name of this experience was Perform Water, financed by the region and so on. And we had, if I'm not wrong, 12 or 15 pilot plants all around our wastewater treatment plants, coordinated by you, Francesca, specifically. And certain of this technology will be industrialized, certain probably not, but it was a fantastic opportunity to try to insert innovation into our plants with the know-how and the skills of somebody better than water operators. I was referring before to the water, energy, food nexus. I won't give you numbers because I'm not working with Gruppo Cap today, but in any case, this is the Peschiera wastewater treatment plant, almost 500,000 equivalent population, with an anaerobic digester. Today, we auto-produce 35%, 40% of the energy we need for the wastewater treatment plants. If we want to reach the neutrality, I mean, not easy, apart if we will have disruptive innovation on energy extraction from anaerobic digester. But all around this plant, there are certain crops from fields owned by Manzoni. It was Leonardo da Vinci, Manzoni, not the real one. Unfortunately, a relative of him with quite, I mean, priority, a big priority on money and not only on literature. But in any case, this agriculture has no water. I mean, in 2020, he called us, I have no water. I don't know how to do for my crops. Can you support me? And we started supporting him with direct wastewater reuse. And around this little project, we also with Polytechnic and other university, by the way, we have an in Horizon 2020 funding. But the idea was to, optimize the use of wastewater for agricultural purposes. Easy, everywhere in the world. On the other side, it was to maximize the use of nutrients, phosphorus and nitrogen for agricultural purposes. Okay, easy also, using digitalization and trying to push to the local communities and to the environmental communities, ARPA, ARPA, which was not, they don't love wastewater reuse. So the aim was to try to convince them to push this kind of project. On the other side, working with this Manzoni, we started thinking about something which is, I know that probably on the scientific point of view is not interesting, but it's agrivoltaic. So here the idea was, if we want to solve a problem for Mr. Manzoni, and if we want to solve a problem for us, we have to try to have all the needs on the same table and to try to find the right balance. I want energy, because anaerobic digester is not enough. You want water and nutrients. Can we do something together? What sometimes we call industrial symbiosis. So trying to match the needs of different industries, organic waste industry with wastewater treatment plants, agriculture with the wastewater treatment plants, and so on. This is my idea on the water world. On the gas, in the next 7 minutes, which are the challenges we are facing? Of course, we all know that the methane as we have today will decrease in the next years. I don't know when. The last year we had a decrease of 5% of the consumptions. Probably in 50 years, you will not use the methane from a fossil as a fossil fuel, but nobody knows when it will happen. On the other side, we know that you see last year when the gas prices increased, it was problematic for everybody on an industrial point of view, on a civil point of view, because we are not ready to dismiss gas or to decrease the gas production, because this will impact on a cost point of view. And on the other side, we had several problems with the security of supply, because we are not producer. The first biomethane plant, remember, was in 2016-17. We are not ready to substitute fossil gas with renewable gas, at least in Italy. So on an Italian gas industry point of view, we know that we have to face, with these 3 challenges, knowing that biomethane will increase, knowing that hydrogen will increase, not in the same way, probably, and knowing that you will reduce your gas consumptions. This is for sure will happen. What we have to do as gas industry? First of all, we have to decide if to invest or not to invest on the existing assets. Because if in 30 years fossil gas will disappear, what we will do with our existing pipes? Do we have to invest or not? And if we have to invest, we will invest substituting, or we will use innovative algorithms in order to understand where to invest. Second, we have to be ready, accept that in the existing pipes, some new gas will arise. We know, for example, as Italgas, that we know. I can tell you that we received 400 requests of connection from biomethane producers this year. We didn't receive request from hydrogen producer, but we know that in a certain transition period, 30 years, 35, 50, 20, we don't know, we will have to use the existing pipes in order to deal with different gases. And this is a big challenge. It's not so easy because today, as gas industry, we receive gas from a few points, North, Algeria, whatever. Only one company almost in charge of giving us this gas, SNAM, always the same quality, more or less, and basically no fluctuation, apart last year. While dealing with biomethane producers, we will have hundreds and hundreds of different producers, different quality, because, yes, I know that on a scientific point of view, biomethane is biomethane, but from organic waste or from wastewater, and if the plant is working well or not well, will impact on the quality of biomethane, with a lot of flexibility. Because I was a biomethane plant operator, and sometimes my guys called me, Andrea, the plant is off. But on a network point of view, if the plant is off, you can't switch to the Russian gas in a few seconds. So we have to think about how to make our network digital. Digitalization is a priority not only for the water industry, but imagine in the gas industry, now we have to pass to a static network to a really dynamic network in order to balance quality and quantities in real time. So this is a 2 billion euro investment in terms of Italian market on the gas industry. Digitalization on the network in order to give them flexibility. We are investing, of course, in some pilot plants for producing hydrogen. We have a plant under permit in Sardinia. It's a little plant. I can give you more information if you want. And this will tell us as a gas operator how the hydrogen will impact on our existing plant pipes, and not only. But if I look, and 3 minutes, my presentation is finished in 3 minutes. So if I look to the next challenge, we will have, this is from McKinsey, for sure, connectivity. Digitalization means that all our equipment has to communicate. I was in Faenza during the flood because we were impacted. Plant, everything digital, SCADA, control room. Little problem. The telecom providers were down. What you can do is the network, the existing network, telco network enough? All our objects will speak with the control room. Today they are doing it, and in the future it will push always more. Are we ready to have a telco shutdown? On one side. On the other side, big opportunity, in my opinion, because this is McKinsey, but Andrea was trying to give opinion. Automation. I mean, I'm an engineer. I know that engineers are going right well on the professional market, but we need technicians, specialized technicians. And we don't have specialized technicians. We'll have to automate certain processes because we will not find specialized technicians in the future. We have to push on artificial intelligence or programming and on materials. It was interesting for me, the other presentation, and on materials I expect a lot even from university in order to try to understand if we can treat better with the new materials in our existing civil infrastructure. When I look at wastewater treatment plants, we are testing something with you, but I expect a lot. As Andrea Lanuzza, I'm quite curious regarding direct CO2 capture, because as a citizen, I think that not everywhere we will be ready to face the challenge we have in terms of CO2 reduction for 2050. 2050 is tomorrow. 2035 is now. If you look at the permit, the incineration, the fluidized bed incineration plant of sewage sludge need 4 years in order to add the permit and 2 years for the constructions. So 2035 is tomorrow. So it's my opinion that we have to push also, unfortunately, on the opposite side. And on this point of view, if I can have the opportunity from you to receive some materials and to study, it will be a big interest for me. And the last challenge, people. We need the engineers, we need technicians, and we need the companies to make less blah, blah, blah on people and to try to be, to work, the HR department, I would like the HR departments to work as the operations department and not to sell dreams and not facts.
Thank you very much, Andrea, for a very interesting talk. We have time for a couple of questions. You want to start?
May I ask a question to Andrea? What do you think about getting energy neutrality in wastewater treatment plants? You think it's realistic, the time schedule defined by the last version of the Urban Wastewater Directive? Because according to some people in it's quite unrealistic to get it.
No, it's completely unrealistic in the sense that
exactly
on the little plants, it's impossible. And in Italy, you have a lot of little plants.
Yeah. So how can we convince the European Commission that they are posing unrealistic schedule for energy neutrality in wastewater treatment plants?
I think there is a monitoring period. If they can visit certain of our, Andrea Liscioni and Nosedo is fantastic.
Yeah.
They only have to visit that fantastic plant and understand that even if with the best technologies today is
impossible to reach.
It's impossible. Apart if you start working with other industries. So you need agrivoltaics, you need to put organic waste or liquids or whatever into your anaerobic digester and so on. Only with the municipal wastewater, it's impossible. And if you, because somebody tells you, yes, okay, but because you have too many infiltrations of, but 1.5 billion euros of investment of on the stormwater only for Milan, you need 15,
so
20
industrial
years.
symbiosis is the answer, but not all can afford to get, not all the wastewater treatment plants in Italy can afford to have an industrial symbiosis. So it's impossible in the large scale. So only few cases can do it. Some situations are more favorable, others are not.
Yeah, I agree with you.
Thank you. Are there any other questions? Please, Stefano.
Thank you for the very good presentation, and very interesting about that. I want to ask you about the energy, the diffuse energy on the net, because the problem of digitalization of the net implies the fact that you have to feed the sensor, the transmission of the data, and so on. Do you think about battery or other things about this to overcome this problem?
In certain case, batteries we are using. In certain case, micro turbines. For example, on wastewater or drinking water, we are using them. Solar panels and so on. We have no other technologies now to be used. But in any case, so at least in the gas, I'm thinking about installing on the critical equipments, because you will have a lot of sensors everywhere, sometimes only for optimization, sometimes for security. On the critical equipments, we will install batteries, because, for example, in Faenza, we had also a shutdown, and dual SIM plus radio. We need the redundancy in order to have resilience.
Okay, because then there is a presentation about this problem, and I think you may be interesting about that.
For sure.
Okay, thank you very much. We have time for one more question, if there is. Yes, please.
Francesca, remember, I am not a student.
Well, as this is one of the, as you know, as this is one of the research field that we are quite dealing with, that is synthetic methane by biological processes involving hydrogen. And we are in close cooperation with other colleagues from other departments that are doing the same on the catalytic. And to my surprise, I understood that, okay, the bio has a lot of advantages, at least in medium, talking with them in medium sizes, like the one typical sizes in a wastewater treatment plant. The real problem is the cost of hydrogen. So, which is green hydrogen. So, which is your, I know that it's not, anyone is really, can really make a reasonable estimation, but how do you see the market of green hydrogen produced by electrolyzers in the next years in terms of cost? So the renewable, the excess, the non-programmable renewable energy cost will be somehow supported. In Denmark, they said it's free. I don't think free it's possible, but
on one side, CO2 also is a cost. So if you use as impresso hydrogen to be coupled with CO2 in order to avoid that CO2, when you have a business plan, you have to take into consideration also the CO2 cost. First answer, which was not the answer you were looking for, meaning that in that cases, I think that on an economical point of view or economical environmental point of view, you will have a break even in a certain way. On the other side, the price will decrease because we are investing, I mean, we will invest a lot on this technology, and by definition of industry, this price will decrease, but need to receive incentives. Even on the production of biomethane, we received a lot of incentives. I mean, and they are renewing because we were not able to build the plant during the duration of the incentive directive. We received a lot of incentives for the 110%, I mean, for the renewal of the buildings. So if they gave incentive for the renewal of the buildings, why they should not give incentive for this kind of industry? I'm not sure we'll arrive at the break-even in the medium term, 10 years. I'm not sure we will be able to do it, but I know less than you. But yes, it will work in some years, and it has to be supported by incentives. By the way, biomethane, without incentives and with the price of gas at 0.2 euro per standard cubic meter, will not be affordable. Today, the price is at 0.5, 0.4, 0.6. It's affordable. The price of the gas, I don't expect that it will decrease. So biomethane, probably today, if you already have anaerobic digesters and you don't have to build new anaerobic digester, it's okay. And to the hydrogen will happen, I hope, the same. I hope.
Oh, thank you very much, Andrea, and we thank you again for your presentation and for answering all these questions. Thank you. Now we can have a break. We can restart in 20 minutes.
Okay, so now we can start with the second part of our seminar, and we will have 6 talks from 6 young researchers of the department. The first one is Dalila Vescovi, and she will present advanced lubricant properties of granular materials between sliding interfaces. You have 15 minutes, and you can decide here or I think. Okay.
Thank you. Good morning, everybody. My name is Dalila Vescovi. I'm a junior researcher at the hydraulic engineering section. And my work focuses on granular materials, granular flows. The title of my presentation of today is Advanced Lubricant Properties of Granular Materials Between Sliding Interfaces. And this work is funded by European EIC Pathfinder grant, and I'm supported by a national PON project. So the driving concept of this project is superlubricity, which is a still ideal state of ultra-low friction between two rough sliding surfaces. And the long-term idea is to use colloidal particles to produce a dynamic network of superlubric contacts between sliding interfaces. So it is crucial to understand how the colloidal particles interact each other and behave macroscopically when shared between rough surfaces which are in contact. And the aim, let's say, my role in this big 4 years project is to visualize the contact network of colloids and to study the shear resistance and the friction of colloidal granular systems by means of particle simulations. So why I am presenting this work today in the framework of this seminar? Because an estimated 25% of world energy consumption is due to friction between moving parts. And minimizing friction and shear resistance is crucial to save energy and to reduce wear and tear in machinery in both industrial and environmental technologies. As an example, in the framework of civil and environmental engineering, superlubrication could improve significantly the durability of gears and bearing systems of wind turbines, for example. Okay, so superlubricity is the ultimate goal of this project, which is currently at the beginning and still far from realistic applications, but is still in a basic research stage. Moreover, colloids are collections of small particles suspended in a liquid. But in this first stage of the research, we focus on an ideal colloid, which is a dry granular material, so without any liquid, composed of identical frictionless spheres, sheared between two rough surfaces which move in opposite directions in the absence of gravity and under load control. So the goal of my research is to investigate the role of particle properties and the roughness of the boundaries on the collective behavior of the colloidal granular medium by means of discrete particle simulations, and in particular the goal is to find the best combination of mechanical and geometrical parameters to drastically reduce friction in between sliding surfaces. Okay, so just a few words about the numerical method we have used for our simulations, which is known as discrete element method and is based on a discontinuum mechanic approach. In the EM, a granular material is assumed to be a collection of discrete particles which interact through contact forces. And the particles are soft, non-deformable spheres which are allowed to overlap. And in such a way, the contacts, the collisions among particles are not instantaneous, but take a finite time. So at any time step of the simulation, once all the contacts between particles are detected, the contact forces are computed, and finally the Newton's equation of motion for all particles are numerically integrated. And different methods exist based on different definitions of the contact forces. In our simulations, we have adopted the standard linear spring dashpot model, where the contact force between particles is defined as the sum of two contributions, a linear repulsive elastic force and a dissipative contribution named damping, which accounts for the energy lost during each contact. Now, the micromechanical properties to be assigned to each particle in a DEM code as an input are the particle diameter, density, elastic stiffness, and this damping coefficient. The damping coefficient is actually related to another key parameter, which is called the restitution coefficient, defined as the ratio of pre to post collisional relative velocities between two colliding particles. And this accounts really for the energy lost during a collision. So tells about the inelasticity of a contact. We have used open source DM code to simulate a non-homogeneous granular flow of a collection of n frictionless spheres sheared between two rough surfaces distant of h and moving at constant velocity in opposite direction. The walls are made rough, bumpy, by gluing spheres in regular arrays, and the spheres at the wall, the orange ones, are characterized by the same mechanical properties of the moving spheres, but may have different diameter. And the ratio of the sphere to the moving particle diameter defines the bumpiness of the walls. Simulations are done under load control, so constant pressure conditions. So we apply a constant vertical load to both top and bottom walls. And we let the two boundaries free to move up and down and to adapt to the imposed load, as you can see in this movie, which is a typical simulation. Periodic boundary conditions are applied in the shearing and transversal direction, and we focus on the steady state. So in each simulation, we set the mechanical properties of the particles, the roughness of the walls, the vertical load, and the shearing velocity. And we measure the concentration of the granular system, so the density, even locally, and the macroscopic friction, which is defined as the ratio of the horizontal to the vertical force on the walls. We have studied the influence of three quantities, which are the restitution coefficient, so the inelasticity of the particles, of the collisions, the applied vertical load, and the roughness of the walls through the diameter of the glued particles at the walls. So let's start with some of the results. First, we have investigated the role of the restitution coefficient. In this slide, I show you two simulations where particles, where we have used two different restitution coefficients for the particles. So on the right, the restitution coefficient is very high, 0.8. That means that only the 20% of the energy of the particles is lost during collisions. So particles are almost elastic. Starting from a given initial condition and applying our shearing protocol, we observe that the system dilates during shearing so that the mean concentration, plotted here on the left, decreases in time, the blue curve, till reaching the steady state in a quite dilute condition. On the opposite, on the left, the restitution coefficient is much smaller, 0.4. That means that 60% of the energy of the particles is lost during collisions, and particles are very inelastic. Starting from the same initial conditions and applying the same shearing protocol, the system initially dilates, the concentration decreases, but then it compacts, as you can see now. Yeah. So the average concentration at the steady state is much larger. The particles are much less energetic with respect to the previous case. So starting from the same initial conditions and applying the same shearing protocols, we reach two very different steady states. It is interesting to visualize the local distribution of the concentration, so the vertical profiles of the concentration for the two systems. In the case of almost elastic particles, the blue case, the system is very non-homogeneous, the density is very non-homogeneous, whereas in the case of small restitution, the red case, the system is very dense in a central region with a very high value of the concentration, and this central region is surrounded, far from the boundaries, is surrounded by two very dilute zones called shear bands, which are characterized by very low shear resistance. And this, it will be clear later on, will affect strongly the friction of the system. So now I showed you just two simulations, but we have performed 6, so considering 6 different values of the restitution coefficient. And we observed that the mean concentration of the system at the steady state increases by decreasing the restitution, as shown here, where the concentration is plotted against the restitution coefficient. More interesting is the effect of the restitution coefficient on the friction of the shearing system at the steady state, here plotted on the right. What we can conclude is that the systems of very inelastic particles, that is a small restitution coefficient, are very dense and characterized by low shear resistance, so low macroscopic friction, which is the goal of our research, to get to very small value of the friction. Now, we have investigated even the role of the applied vertical load with the aim of reduce the friction, and we have considered sets of simulations with larger and smaller values of the applied vertical load. And the larger the imposed load, the larger the concentration and also the friction. So in order to focus on small resistance, we consider the smallest applied load we have considered, and we now investigate the role of the roughness of the boundaries. Considering 3 different walls, kind of walls, bumpy walls, where the glued particles have diameter 1, 1/2, and 1/4 the moving particles. The roughness seems not to influence the concentration of the systems. As you can see in this slide, the 3 curves are very similar to each other. Instead, there is a big influence on the of the roughness on the friction, and a strong lubrication effect takes place when using small bumpiness, small roughness, even at large restitution. So we are still far from super lubricity, which is defined as friction smaller than 0.01, but we are approaching it. So concluding, for now, what we observed is that in order to get small friction, small shear resistance, we need to use small bumpiness, small restitution coefficient, and small loads. And for the future, we plan to use polydispersed particles in order to get small friction even at more realistic applied loads, and for sure to mimic the presence of a liquid. So thanks for your attention.
Thank you. Thanks a lot, Dalila. If we have some time for some questions. Yes, please.
Okay, thank you, Dalila, for your presentation. Just a curiosity, when you show the dependence on the friction on the applied vertical load, can you go back to the slide? Yeah. What do you expect if you increase again FZ? Because I see that there is an increase. So do you expect to reach a plateau or?
Thank you, Pietro. That's an interesting question. What we observed increasing the vertical load is that the system is so dense that crystallizes. So yes, we go to a plateau because at the end we have really a crystal. The spheres become at rest at the end.
But only in the central part?
No, all of them.
All of them?
All of them.
Okay. Thank you.
Thanks.
Yes, I have a question concerning the periodic boundary conditions. Because you analyze this representative volume with discrete particles. And so how do you need to have a specific arrangement of spheres on the left and right boundary to apply this periodicity, or how do you do it?
Let's see if I'm able to run the movie. Yeah. Periodic boundaries means that in numerical simulations, your particles going out from the system on the right come back on the left. Mm-hmm. And so it's a sort of infinite length of the domain in the X and Y direction, which is unrealistic for sure, but it's a way to get rid of the dependency on horizontal space, let's say, and to focus only on the vertical distribution. But in real application is a sort of steady state between two very long planes.
Okay, thank you.
Thanks, Dalila. I think we can move on to the next speaker, which is Davide Chiarelli. And he will speak about the circular economy of blue water, potential application of brackish water in agriculture.
Good morning to everyone. I'm Davide Chiarelli. I'm the researcher here at ENergetica, and today I'm going to speak about the circular economy of blue water. So potential application of blue water in agriculture. What we are observing is an increasing demand of crop production for different reasons, as the increase in population, so more people that we have to feed, but at the same time, an increase in crop production also for the energy sector, as the biofuel policy, the livestock that is increasing because the shift in the diet. So the idea is that somehow we need to have more agricultural production, and to do that, we have to try to use better the area that is currently harvested. At the moment, we have that only 20% of the total area is irrigated, and 77% is rainfed. That means that depend only on precipitation. A big opportunity can come if we try to irrigate those rainfed areas if there is a lack of water. So the water for irrigation is not provided. In this case, there can be two different conditions. One is that the water is available, but there are not the infrastructure in order to provide this water, or the water is not physically available. So in one case, we are in an economic water scarcity condition. In the other case, we are in a physical water scarce condition. What I'm trying to focus with this presentation and what can be the help with this presentation is especially for those physical water scarce condition areas. So what we try to do is to see if it's somehow possible to increase the availability of water. How? By try to using non-conventional water. So try to use better or to reuse the water that we have. Before going with the presentation, I just give you some definition that will help us understanding a few terms that are used, and so mainly a plant in order to grow need of water. This water can come from precipitation that is stored into the soil, and so we speak of green water. Or by the contrary, if precipitation alone is not able to satisfy the entire crop water demand, so the entire water that the plant needs, we can apply this water for irrigation. In this case, we speak of blue water, so the water that we take from fresh water or from the groundwater and we provide with irrigation. The way in which we provide irrigation can be different depending on the system, and so we can have surface irrigation when we are applying the water due to gravity on the field. We can have sprinkler irrigation, and so we recreate an artificial rainfall, or we can have drip irrigation, so a system in which a drop of water is just left where the root apparatus of the plant is. What we try to do is to see if it's possible to use the non-conventional water in order to provide the water needed by the plant. The definition of non-conventional water change. In any case, we can consider as all the water, as non-conventional water, all the water that need a treatment before being used, where need a technology, where this technology can be a treatment, so for example, the salinization plant or a wastewater treatment system, or a technology as can be the fog collector or other collector in order to harvest water. My focus today is especially on brackish water, so a water with a certain concentration of salt that can be coming both from the salinization plant or from the extraction of groundwater, where brackish water can be classified depending on the soil content as slightly brackish water that is and can be commonly used for irrigation, but we can have also brackish water, moderate saline water, and saline water. The idea is try to see if it's somehow possible to use this type of water for irrigation, where using this type of water for irrigation, for sure is possible. We need to see which can be the effect of different type of salinity and concentration of salt in the water. To do so, we developed a model. We already had an hydrological model that I developed during my PhD thesis, that is the WATNITS model. And then to this model that solves an hydrological balance, we try to add a salt model, so a model that is able to make also a mass balance equation of salt. In this way, we are able to quantify by one side the amount of water that is needed by the plant, split between green water and blue water, so the water that we need to apply with irrigation, and in a specific calculation also on the soil concentration, the electric conductivity, so that we can try to see if this blue water is needed to be fresh water or somehow we can mix with salty water. The idea is that, and here I do not enter too much into detail, but we have by one side a water balance equation that solves the mass balance of water into the soil. To this we add a salt balance, where a specific attention can be provided also to the leaching water. So some additional water that we need to add in order to remove the salt that are concentrated in the first layer of the soil where the root apparatus of the plant can uptake water. Clearly, there is a different type of plant that react in a different way to the soil concentration in the soil. And so also using brackish water, so for sure, is strictly related also to the type of plant that we have. Wheat, barley are for sure more tolerant to other crops as maize, that by the contrary is more sensible to the salinity of the soil. More salt is in the soil, less or more difficult is for the plant to extract water. So we want to avoid this, especially for the salt-sensitive crop. The idea of this research is try to make this analysis for at least 17 crops, but we can also simulate more, both in open field and protected cultivation, in soil and soilless system, this is especially for protected cultivation, under a different type of irrigation system. So we saw furrow, sprinkler, drip, but at the same time also hydroponic and so on, with the idea always to have the blue water, the green water, and the salt concentration in the area. The presentation of today and the results that I'm going to focus are only based on wheat in an open field in a soil, so in a traditional system, for furrow and drip irrigation, that just to catch the way in which this type of brackish water can be used, where brackish water is considered and is provided alone. So we see the effect of applying only brackish water. But we try also to see the effect of applying mixed brackish and fresh water, so in order to reduce the concentration of the water that we add on the field, and then the importance of leaching, so to add more water into the soil so that this water can percolate into the soil, but at the same time can remove part of the salt that are concentrated in that area. The application is provided for the case study of Egypt, where for sure there is a problem related to water scarcity, so where fresh water is not abundant. Agriculture is one of the main sectors for the production, but at the same time also for the economy of the entire country, and where there is problem of salinity. So for sure can be an interesting case study. And again, the result that we see mainly focus on wheat, but at the same time we run also all the other crops. The idea now is that we try to compare different type of water application, and the graph report the salt concentration that we have on the soil that are reported in red, the amount of water that we need to apply over the field with irrigation, that are the column that can be green, yellow, or blue. And finally, the most important parameter that we need to focus on is the KS, that is a salty coefficient parameter that provides an idea of the stress of the plant. Lower is this value, means that the plant suffers more, and so we can expect a lower yield. If it's close to 1, that means that the plant can grow without any stress. For sure, we see that if we use different, in this case, we are using only brackish water for irrigation with different concentration. We have 1.2 on the top left, 2.5, 5, and 7.5. What we can see is, and the crop is wheat, so a crop that starts to be sensitive to soil concentration when it's higher than 8 decisiemens per meter. What we see is that we are using on water that have 1.2 or 2.5 decisiemens per meter. The crop can grow mostly without any stress. By the contrary, as soon as we add the soil concentration to 5 or to 7.5, the KS parameter is 0.5 or 0.12. That means that we add only 50% or roughly 10% of the maximum yield that we can obtain. So for sure, it's true that we can try to see if brackish water can be applied, but we cannot use seawater at all for irrigation because otherwise we damage the crop. Now, among the possible concentration that we can use, we try to see which is the best way in which to apply this type of water. And so we try to compare different strategies. Now, we compare a concentration equal to 2.5 decisiemens per meter for the brackish water consideration. And fresh water, clearly we consider water that has a lower concentration. For sure, we see that fresh water do not change that much the soil concentration. It is the best that we can use. But in those cases in which this is not available, let's see what happened with brackish irrigation. As we saw before, only brackish irrigation with wheat in Egypt do not create a sensible reduction in crop yield, at least in this specific point that is just north to the Cairo, so in the Delta area. And so mixed irrigation, in this case, you see that is 0 in terms of fresh water mixed with brackish water. Clearly, if we repeat the same for maize, for example, you see that necessarily you need to mix water if you don't want to reduce that much the yield. And finally, interesting results is obtained as soon as we mix brackish water with leaching, because in this case, we are able to have again a KS that is equal to 1. So we can expect to have the maximum growth of the plant without any reduction by using the same amount of water. Clearly, we need to find a trade-off between the use of brackish water that by one side reduces the crop yield and the water that we have available. Again, interesting can be not only to find the best way in which to mix or to provide brackish water and fresh water, but also the type of system, the irrigation system that we are using. In this case, we are comparing surface, so traditional irrigation system in which we apply the water by gravity over the field, with drip irrigation system. So just apply a drop of water where the water is needed. Again, if we compare fresh water, there is no reduction in the crop yield expected for the plant because clearly fresh water is not increasing that much the presence of salt in the soil. What is important to notice is the quantity of water that we need to apply with irrigation. In one case, it's mostly 2,000 millimeter. In the other case, it's only 577 millimeters. So there is a strong reduction in the amount of water that we need to apply. When we move to the right side, so when we compare the condition of brackish water use, for sure you see that freshwater surface irrigation system has a better condition than drip irrigation. That mostly because when I add water with a surface system, I add more water than the water that is needed, more water than the water that can be stored into the soil, and so you have depercolation, part of the salt are removed. In the case of drip irrigation, no. So if I'm using water that has a certain content of salt, this salt stay in the soil. The next, so the next step is try to see and to combine drip irrigation system with leaching. So try to add again also with drip irrigation a little bit more water in order to remove salt concentration. In this case, we see that the KS parameter as soon as we add leaching is increasing. So with this additional water that is just 41 millimeters, so 10% of the water that we will apply with drip irrigation system, we can increase the expected crop yield. And so clearly expect to have more products at the end. Next step is try to apply this the same balance, not just for one point, but to the entire country, at least in those harvested area. We consider suitable the use of brackish water when the yield is not reduced more than 30%. So when the KS mostly is limited to 0.7. In this case, the gray and black pixel represented all the area that is harvested with wheat in Egypt, and the colorful pixel represent the area where brackish water can be used without an intense reduction in the yield. If we are considering only brackish water, what we have is that 7% of the total area of the country can receive this type of water without have this big reduction in terms of crop yield. For wheat, it's even 11%, 13% in terms of barley. And the amount of the brackish water that we will use is equal to 3.3 cubic kilometer per year. It's more or less 6% of the blue water withdrawal for agriculture in Egypt. So for sure, there can be a reduction in the freshwater use, but for sure there is this brackish water that needs to be generated and applied. By try to consider a situation in which we apply brackish water with leaching, so in this case we have an additional water for leaching, we have that 16% of the total area can be irrigated with this type of system. If in the case of wheat, we have 35% of the total pixel that can receive brackish water plus the additional water for leaching. In this case, the total amount of brackish water that is needed is around 10 cubic kilometer per year. And so this corresponds to about 18% of the blue water used in agriculture in Egypt and 0.3 of fresh water for leaching. So there is a small amount of fresh water that is needed, but for sure less than in the normal situation. So what we can say is that brackish water can represent a possibility to support irrigation. Clearly, not all the water can be used directly, otherwise the yield are too much reduced or even the crop completely died. There should be a trade-off analysis in order to check where and if it's really convenient to use this type of water, because at the moment we are just looking at the amount of water that is needed, but brackish water can require energy, can be costly, and so clearly we need to check if and how this type of water can be used, but at least in terms of water, we can say that part of the area of the country can be, this type of water can be suitable, and the most promising system will be the combination of drip irrigation with leaching. At the moment, we have one paper submitted on this topic, one under internal revision, and with this I just conclude. Just have a list of the reference, few of the projects that are supporting this analysis, and so thanks for the attention.
Thanks, Davide. Do you have questions? Giovanni.
Okay, thank you, Davide, for the presentation. So the question is about the impact of the soil. So what is the soil type that you consider in this analysis? And do you think that soil management, I mean, the increase of organic matter in the soil can enhance the crop tolerance to salinity?
For what concerns the soil, we are considering a global data set that report for each pixel the exact soil that we have. So we have the simulation that reflect the actual soil that we are observing in the area. For sure, the soil impacts a lot, especially for what concerns the way in which the water is stored in the soil and move away, because the percolation plays an important role in removing the salt that is in the soil. So higher is the deep percolation, and better it is because we remove part of the salt. By the contrary, if the pore in the soil are bigger, is also less the water that can be stored. And so again, it's a trade-off between the water that can be available by the plant and the salt that is concentrated into the soil. So this clearly depends on the type of soil in that specific location. Something better when we consider protected cultivation, and so like hydroponic system. In this case, sometimes the roots are directly in the growing in the water or in some porous system. And in this case, even if we are using salty water, the soil concentration can be reduced.
Thanks. Other questions? Okay, yes, thanks.
Hi, thank you for the presentation. I was just one question. I was thinking, do you think that the use of seawater, salty water, could have an effect also on the irrigation system? Or, I mean, the actual irrigation system is suitable for the use of seawater? Or
For what concerns surface irrigation, there should not be big problem. The big problem are for drip irrigation system, because one of the biggest problem that we can encounter is the clogging of the system. And so salty water, as soon as we have just one drop of water falling down, can be clogged by the salt that is concentrated in that area. So for sure, for drip irrigation can be tricky, the use of this type of water.
Thanks. A quick question. For the salt stress and water stress, I imagine you use the FAO approach, right? So when you quantify the volume of water that you need to provide to the crops, you use, your objective was to have like potential evapotranspiration, or based on soil moistures that you made varies, because these of course can change the water also compared to water availability then that you can have.
Depend on the type of simulation that we want to carry out. If it's a rain-fed condition, so we are not providing water for irrigation, clearly we consider the actual evapotranspiration that is reduced, so less water is used, depending also on the water that is available into the soil. So we consider the KS parameter that reduces the crop evapotranspiration. Well, when we are using irrigation, clearly we consider that we want to obtain the maximum yield, and so we provide all the time the water that is needed, and so the water is there. In the case of salt, we do not have only the coefficient depending on the water present in the soil, but we add the salt coefficient, the KS salt that you see before. And in this case, even if you apply irrigation, there can be some condition of stress due to salt. So the maximum yield is not reached, the maximum crop evapotranspiration is not reached.
Thank you. I think we can move on to the next one. Thanks. Thanks, Davide. We move on now to Giacomo Ferrarese, and he presents innovative technologies in the fight for water distribution and sustainability. You have 15 minutes, more or less.
Okay. So, good morning, everyone. Thank you for being here. I'm Giacomo Ferrarese. I'm a researcher here at the DICA. Closer. Okay. So, what I would like to discuss today with you is about the role of innovative technologies in the fight for water distribution sustainability. First of all, I would like to introduce you an example. This is the network of Milan, just to understand the complexity of a water distribution system. We have long pipes that are interconnected each other. We can have pumping station, we can have reservoir. Most of all, I would like you to see the amount of water, so of source that is used by these kind of water distribution systems, and the energy also that is consumed by these kind of distribution networks. And we can see that sustainability in this context can be seen from 2 points of view. The first one, that is environmental. That means I would like to reduce the withdrawal of water that is used by the network. And the second one is energetic. I would like to reduce the energy or implement some kind of solution that reduce the energy that is used by the network. So we can have different kind of networks devoted to several users. The users can be civil, industrial, or agricultural, but all those networks share some issues, some common issues that are basically the need of renovation because they are aging. We have networks, particularly for civil application, that have more than 50 years. The change of habits of the users caused primarily by climate change and population growth, and also the lack of information, because many times utility, so who has care of the management of the network, doesn't know precisely how the layout of the network, and they don't have precise information on how the network is working. The importance of water and of the access of water for people is also underlined by the central role in one of the United Nations Sustainable Development Goals. So what can we do to try to solve some of those issues that we have seen in the previous slide? We can act on the infrastructure, so we can change pipes, we can increase the reservoir, so we can act directly on static parts of the network, on the infrastructure. We can add some passive components like sensors to add information, so to let the management, so the utility, to have more information about how the network is effectively working. And we can add also some active components like pumps and valves. Naturally, the active components can act on many optimization objectives. So we can achieve leakage reduction, we can reduce maintenance costs and planning, we can increase the water management system in general. I would like to focus on precisely on valves, so on how control valves can be used in water distribution system to improve its sustainability. Let me show a simple example of a network or a sector of a network. We can know about how the pressure is behaving in the network. So each node of the network have a precise pressure. We have the inlet, and a fluctuating pressure at the inlet, and also knowing the pressure distribution in all the network, we can know that there is a node that is the most critical, that has the minimum pressure. So you know that to serve the user effectively, we have to achieve in all the nodes of a network a minimum pressure that is necessary to let the user use effectively the water. And why we would like to introduce in such kind of network a control valve. We would like to introduce this kind of technology, this kind of device, to normalize the pressure in the network in such a way that the minimum pressure at each node of the network is the closer possible to the reference pressure, so the minimum pressure that is necessary to serve the users. And so we are introducing at the inlet of a sector of a big network or at the entrance of a water distribution network, a device that acts as a pressure reducer. That means I am dissipating energy at the entrance of the sector. In the simple case I showed you, it seems that is a simple task to know where it is possible to install such kind of device. But if we think of a real network, so a very diffused network, a big one with a high number of nodes and pipes, each of the pipes can be the place where the device to control the flow and the pressure can be installed. So this is not a simple problem. We have done a study using, for example, the particle swarm optimization to understand, to limit the search space. So we are not able to make a simulation to know each time where it is more effective to place this kind of device. We use this kind of algorithm that is useful to find the best solution without doing all the simulation of all the cases possible. I don't want to go deep in this topic. I would like also just to show you the results of the study. So we here you can see some results. The red line is the leakage hour per hour in the network we have seen just before, the big one. And we have used this algorithm to find the best placement for PRV and the best setting of this PRV. So which is the condition, the working condition of the device to get always the minimum pressure in the network. So the optimal solution. And we used different objective functions based on different constraints, basically. And we find that it is possible just installing 3 valves inside of the network to reduce the leakages of about 15%. This means that the first objective of sustainability, so the one dedicated to the environment, I want to limit the water withdrawal, can be obtained simply and without acting just on the network, installing devices that dissipates energy in the network. In fact, we have said before that any of these devices is going to reduce the pressure, and to do this, it needs to dissipate energy. So in another study, we have collected data from several plants considering already installed control valves to see how much energy is dissipated by this kind of devices. And you can see here the results of the analysis. You can see in the green part The first thing that you can see is that the amount of energy, the total amount of energy that is dissipated is not negligible because it's a high amount of energy. And the second thing is that we split more or less 50% between the green part and the blue part. The green part are valves that dissipate a small quantity of energy. So a lot of valves that dissipates a small quantity of energy. And the blue part instead are valves that dissipate a few valves that dissipate a lot of energy. This means that from the point of view of energy optimization, we can do two different things. The first, for the blue side, we can think about energy production. We can substitute those kind of devices where energy is dissipated and create, basically extract energy with the best efficiency possible. So we can install small turbines, PAT that are inverse pumps, counter pressure Pelton, cross flow turbines, and so on. But why I talk about these high efficiency energy extraction just for those blue cases? Because there is a limit below which the production of energy, production, I mean, I produce energy and then I sell energy because it's a matter of economics. And below a certain limit, the economic feasibility doesn't stand. So for sure, I've made a study considering all these cases, and we found that above about 3.5 kilowatts, there is feasibility for the installation of PAT systems, so pumps as turbines. And below this limit, we can't recover energy for production. So we can't think about recover energy and sell it to make money. So the question we want to answer is, it is possible to exploit this residual energy that is a large amount because we are thinking about the 50% of the total energy dissipated. Is it possible to do something with this? And which is a technology that can help me doing this? Here, one possible solution is the green valve system that is a patent of Politecnico di Milano that has been developed by the Fluids Lab group in the last years, and which is the objective. The objective is to create not only a device that is able to reduce the pressure and dissipate the energy, but a small part of this energy can be recovered. I can store this energy and use locally. So I don't want to sell it because it has no sense, but I want to use it locally to improve the process. So to add some function, some useful function to the control point, the control node on the network. Those kind of function can be the automatic actuation. I have energy to do so. A dynamic pressure control that can be also remotely operated. I can use also energy for some local use, like the disinfection pump that in some nodes are necessary for the good functioning of the network. Alert managing, real-time monitoring. This is very important because I have energy to make monitoring at high frequency. That is something that using solution like batteries or other kind of energy source, limited energy sources can be achieved. And so this is this technology can be an enabling technology for the creation of some solution that are not possible with simply device to make control of the pressure. This is just the state of the project that the patent has been developed by the Food Lab research group, and it has been licensed. So now the prototype has been engineered by a company. And here you can see the first application on field that has been made 2 weeks ago, more or less. And you can see it's something particular, this installation, because we have the green valve system that is installed in parallel with another valves. But this is very interesting because the energy that is recovered by the valve is used also to move and to monitor the other valve that is a normal one. So I have more information on the control node, also on parts of the network that are already there. Just to show you which are the next things that we would like to develop, we want to make the step further. That is, okay, one single valve installed in the network is useful for sure. I have more data. The system is more dynamic. I can remotely move it and change the setting and so on. I have data, high frequency data, but which are the possibilities of having a network of these devices that can work together and create the framework to create new management methodologies that are not feasible with other kind of devices, with common devices. We are developing a PhD together with the University of Basilicata, and on that team. Another step is to bring, and is the topic of the PRIN we won 2 weeks ago, 3 weeks ago, I don't remember precisely. That is the transferring of this device that has been developed precisely for the civil network application to irrigation systems that are not so different, but they have precise requirements also from the point of view of the type of users that are involved. So I finished the presentation. Thank you very much for your attention.
Thanks, Giacomo. Do we have questions? No. Paola? No.
Thank you, Giacomo. It's very interesting what you told us. Unfortunately, Andrea is not longer here. I guess
I told him that he should remain, but
yes, I was thinking about our aqueduct system, our EMILEN, I mean, aqueduct system in which the water lost in the network is in the same percentage you showed some minutes ago. And therefore, I think that your solution could solve not only the energetical problem, but even at least to some extent, the problem related to water lost within the network. What do you think about that?
I think that this solution can approach sustainability of water system from precisely those two aspects. The first one that is the same of a common control valve. So I want to reduce pressure, to manage the pressure, to obtain the minimum possible leakages, because leakages are directly affected by the pressure. So if I reduce pressure in the network, average pressure in the network, I reduce also the leakages. Naturally, this is a short-term solution for aqueduct, because I'm installing something, I'm managing the pressure, I reduce the leakages, but I'm not solving the problem. Okay, but this is something that can be done very quickly, and it is effective. And the second point of view is that it uses some energy that you lost. You have to lost, because this energy that you dissipate in the control nodes of the network that you decide is the best one and so on to reduce the leakages is energy that is lost, that you need to throw away. And this is a solution that can use this energy not for selling it, but to add many functions that can be useful for the management of the network.
Other questions?
I have a curiosity on slide 8, maybe. Yeah. Because I was looking at that objective function, which goes up and down.
Yeah.
And it seems, I mean, the optimum solution is at the right end, but no, actually the objective function is larger at iteration.
Yes, this is why there are some constraints on the objective function. So it's not a minimization, but it is searching for a certain value of the solution. So that's
okay,
why
it does
that's
not
why it
always
goes up
satisfy
and down.
the constraints.
Yeah.
I mean, maybe at iteration number 15,
Yes,
not all the constraints are satisfied.
Sorry, this video is not linked directly with a plot. Okay, it's to understand the functioning of the system that is based. Basically, the best solution works like a magnet for the other particles. So for the other solution, so if you find that one of the solution you have calculated is the best one from the point of view of your objective, then the other particle goes toward this solution. Then they have an inertia. So if then the time step after, there is another point that has the best, the new best solution, that particle acts as a magnet, and all the particles follow this solution. It has a lot of drawback, this kind of application, because it is computationally it's heavy, and there is a problem of local minimum. Okay, so if you have some solution that is heavily discontinuous, and you have a lot of local minimum or local best solution, it is a problem to find effectively the best one. You have to create some trick to go around this problem. That is, for example, repetition. So make some repetition of the same problem to see if the minimum is if the best solution found is the same. Or you can constrain, reduce the search space toward what you think it could be the best solution.
Thank you, Giacomo.
Thanks. I have a very quick question. I was wondering if these valves can be installed in any tube lines with any diameter, so if it is constrained for the discharge.
Yes, up to now, they have made 3 sizes. So we have at maximum, I think, 3 inches pipes. And that's why in the application I showed you, it is mounted in parallel with another valve, because the main one is stable, is fixed, and it changed the control during the hours of the day. So there is a setting to change the opening of the big valve, and the small one instead, so the green valve, make the control of the pressure. So make the setting of the pressure precisely.
Yeah, also because the irrigation system and the civil are
different from the point of view of the users. So and the use of the network made by the users.
Thanks a lot. So we can move on to the next one with Matteo Antelmi. He will present groundwater flow energy contribution in BHE systems in an adapted, it's a very difficult title, TRNSYS-type for each VAC system design.
Okay.
Okay, thanks.
Perfect.
Good morning to everyone. Thank you, Chiara. The project I want to discuss today is related to the HVAC system, and is a project that I developed when I was in EURAC research in Bolzano, and is a project that is crossing different topics that and different competencies that I had in my career here at the Politecnico. Here you can see just, sorry, I put the presentation. Here you can see just an overview of the topic that I will discuss today, going through the theory of the HVAC system and going through the numerical modeling of the system to reach the results of the project, and discussing how these results could improve the world of the heat pump system. In general, the geo-exchange system, or are called HVAC system, are heating, ventilation and air conditioning system that are included in the category of the shallow geothermal resources. So we are speaking of low temperature systems. I mean temperatures around 20 or 30 degrees. And this kind of system are consisting of main three elements. The first one is the ground heat exchanger, that could be borehole heat exchangers or wells. The second one is the heat pump, that is increasing the temperature that we can take from the aquifer or from the air. And the third element is the heat distribution system. The operation of that kind of system is quite simple, as you can see from this slide, because, for instance, if you had an installation of borehole heat exchanger, you have a thermal carrier fluid that is flowing down your ground heat exchanger and is able to transfer it with the surrounding aquifer. I mean that the surrounding aquifer generally has a constant temperature, and so you are able to extract or inject heat from the ground to provide heating or cooling to your building, for instance. So the aim is to provide heating and cooling and to exploit the constant resource temperature of the aquifer. The new and quite innovative system is the dual source heat pump system, and is quite innovative because it is able to exploit both sources. For instance, you can exploit both the air source and the ground source. Here you can see that you have mainly two types of operation. One is an alternative use of sources, where you can exploit just or air or ground source, but it's quite common for when you need to refer to it recover. When you are working with heating or cooling of buildings or offices or houses, the drop away is better because the operation is due to lower difference temperature, and at the same time you can exploit the same sources. So you can exploit or the air source or the ground source to give and to provide the heating or cooling to your building. So the aim of this kind of solution is to increase the overall efficiency of the system, going to use the specific, the best and most convenient source in that kind of time. The Fusion Grant project was a project developed together with EURAC and ENEVA, and ENEVA company is located in Bolzano, and this project was due to the problems related to this city for the several climates, because of the summer climates, the ground source heat pump are not good, and but are better than air heat pumps. So it depends from the climate where you can install heat pump with air source or heat pump with ground source. So this solution of dual source heat pump is an excellent solution for the optimal exploitation of the two different thermal sources. But nowadays the control logics are based on fixed rules, so they are not so optimized, let's call it in this way. So the aim of this project was to improve the control logic of this dual source heat pump system. And the main aim of this project was to develop an algorithm based on the model predictive control to increase the efficiency and the energy efficiency of this dual source heat pump system. The first step of this project was to quantify, to classify the heat pump, in the specific the dual source heat pump, and to understand how combining the temperature groundwater with the air temperature, the efficiency and the thermal power provided by the heat pump was varying. So we can, through the test realized in the EURAC laboratory, we carried out a sort of performance map where we can understand the thermal power, the electrical consumption, and so we can know the COP, that is the coefficient of performance of our heat pump. We can know this performance map combining the temperature of the two sources, so combining the temperature source of the air to the temperature source of the groundwater, of the ground. We can understand how the dual source heat pump is going to work well in a more efficient way. This kind of classification of the heat pump provide us the information useful to develop a simulation tool in TRNSYS that is the most energy simulation software used by energy technician to design that kind of system. It is able to simulate energy performance, but this kind of program has some limit due to for the groundwater size, because the element that is a Fortran element that it is reproducing each single element of your HVAC system is related to an algorithm, and the algorithm related to the borehole heat exchanger as a limit to neglect or to not consider in a correct way the role of the groundwater flow. That is very important for the energy performance of your system. So we tried to do the first comparison between TRNSYS and ModFlow, that is a groundwater flow model that is mostly developed to study groundwater problems. And we saw that when the groundwater flow velocity is increasing, TRNSYS code was not able to reproduce this energy increase of the borehole heat exchanger with surrounding aquifer, like ModFlow simulation. That's why TRNSYS has a limit to neglect the flow direction, and it was able just to introduce some kind of radial groundwater. So the percent difference was clear. With ModFlow, we had reached a difference of 150%. In TRNSYS, like 10%. So looking at the literature analysis to try to understand why there was this difference, we developed also different simulation in ModFlow to understand well how was the role of the groundwater flow with increasing velocity. And we try to, as you can see from this graph, you can see that the role of the groundwater flow is very important, because higher is the groundwater flow velocity, higher is the energy due to the exchange between aquifer or ground and your system, that is borehole heat exchanger. Clearly, if you can neglect the groundwater flow, is not wrong, but is too precautionary, is too cautelative. So TRNSYS is quite good for the solution from the hydrogeological point of view, where the groundwater flow is lowest, but it's not good when you have a good groundwater flow velocity. So we adapted the TRNSYS type that related to the borehole heat exchanger to let this approach to introduce the similar approach that ModFlow does also in TRNSYS, and to reproduce the highest energy performance due to the highest groundwater flow velocity. So here you can see the new comparison between TRNSYS with the new type and the mode flow solution. And for each point that is mainly due to the groundwater flow velocity equal to 0.4 meter per day, you can see that the increase of the energy performance between BHE, borehole heat exchangers, and surrounding aquifer was clearly in around the 70% during the heating season or 60% during the cooling season. The type that I created on TRNSYS was validated also against experimental data. These experimental data were coming from my past activity and was related to experimental borehole heat exchangers installed in Lodi, where we monitored all the parameters of this new system. And so I tried to recreate in TRNSYS the real situation and with the estimation of the parameters, and then I compared the exchange energy by the borehole heat exchanger with simulated solution and with the real solution. And the greater difference was reached because the model was agreed to the real data. So this brings us to build a bigger model that was a model reproducing the reference system of our building, consisting of more or less 10 apartments. And the new features introduced in this kind of model was, in the first one, was the new type regarding the borehole heat exchangers, able to reproduce the higher energy performance due to the borehole heat exchanger. The second one was the reproduction of the heat pump, of the dual source heat pump, to combine, to couple the role of the air source and the role of the groundwater source. And the last one was the type related to the control logics under the operation of this heat pump, and try to introduce the different logics to improve the efficiency from the energy point of view of this dual source heat pump system. I don't want to go into the detail of different simulation, but I just want to give you just one example of the different innovative control logic applied to this kind of heat pump. For instance, as you can see here, you can see the energy consumption in 1 month of operation. Simulation time was February, but we can consider it commonly operation. As you can see, the maximum energy consumption are around the 6 p.m. or 7 p.m. when the people comes home. The aim of this logic was to shift the maximum energy loads when the energy cost, the electrical energy cost was lower. In specific, we want to move in the first hour of the afternoon. Why? Because the heat pump was coupled to a photovoltaic system, and as you can know, in the first hours of the afternoon, you have the maximum radiation, the solar radiation, and so we want to load a higher temperature of the thermal energy storage coupled to the heat pump to have to work in a different time. Because thanks to the photovoltaic system, we didn't need to use battery, but we need to use directly the production of energy due to the photovoltaic system to give this energy to the heat pump and to provide, again, heating or cooling to our building in all the hours of the days. In conclusion, the potential developments of this work, I think they are crossing different issues of the environmental and civil and energetic technologies, because there is different possibility to adjust the control logics. For instance, to weather forecast, because as we know the weather forecast of tomorrow, we can also implement a tool in the heat pump to give and to provide heating in the best way, exploiting that maybe tomorrow is more hot than today, and we can give the control logic better to adapt the solution to the heat pump. Or we can cross also the civil technology, looking at the loads variation or the material constituting the building, and to adapt the control logic with the aim to improve the market of the heat pump system. In specific, in this case, is the dual source heat pump system, with the aim also to reach a more energy efficiency of the system, but also with the aim to reduce the electrical energy consumption and mainly the cost of the system. Okay, I finished. Thank you for your attention.
Thanks, Matteo. We have questions. No? Thanks. If not, thank you. We can move on to the next one. Pietro Marveggio. Thanks. Shallow foundation of onshore wind turbine towers toward a sustainable design.
Yeah, thank you so much for your introduction. So, well, first of all, we all agree that we want to get rid of non-renewable energy source, right? So to do this, we have two options. One is to reduce the energy consumption, and Dalila showed us how we can, for example, affect, let's say, the efficiency of some industrial system. Or the other way is to increase the, let's say, exploit more the renewable power source, such as, for example, wind turbine or solar energy. Okay, just to give you a, let's say, a context, we know that the European Commission asked the 27 countries of Europe plus UK, because the target was set before Brexit, to produce at least 43% of electricity from of the demand of the electricity from wind power. We are far from that target, which is close. In particular, this is a chart in which is plot the actual share of wind power, so the percentage of wind power compared on the energetic demand of each country. These data are from Monday. Of course, there is an oscillation, but more or less the trend yearly is something like this. We see that some countries are doing a great job: Germany, Spain, Denmark. So, for example, yesterday Denmark produced more energy rather than its internal demand just by wind. Okay, so the transition is going on. A lot of countries are let's say, a little bit, let's say, stronger than others. Last year, we installed, I mean, in Europe plus UK, we installed a huge number of, in terms of power of wind turbines. This number is increasing compared to the previous year, but still we are very far from the energy goal suggested by European Commission. And in particular, most of the production is set onshore nowadays. Only about 10% is offshore, and this is mainly in UK, which is pushing a lot in this field. Well, the expectation over the previous year is that we are going to install about 20 gigawatt yearly, which is far from the target. But of course, there is a discussion between all the stakeholders on wind energy production on the reason why we are so far from the goal. Probably two are the main reasons. One is related to the cost of installing and maintaining such an infrastructure. And the other way is that probably government are not going to make, well, let's say, some decisions are not pushing in that direction. That's why we have so different, let's say, results in different countries. So, for example, Germany and nowadays also France are pushing in this direction? So are they helping companies consider both in terms of regulation and fundings? But on this aspect, there is not much room for a discussion here in this workshop, but we can do something to reduce the cost of this infrastructure. Okay? So we have several options in terms of, let's say, installing wind turbine. Basically, I'm not going to refer the tower itself or the turbine, which is something, let's say, governed by the technology itself, so more on a mechanical point of view, but I'm going to focusing on the foundation. There are several options when we consider offshore foundation, but in this case, and also because the vast majority, as I show you, are onshore, I'm going to refer to this, and in particular on shallow foundation, okay, which is the other one of the options, pile or shallow foundation. Well, what can we do in this case? Well, that's of course an average value, but more or less a shallow foundation for a wind turbine, it's about 20 meters diameter, so it's a huge concrete structure with an 8 up to 3 meters. Unfortunately, there is no much room in this case to work on the geometry because basically we have to design it in order to avoid the toppling of the structure itself. Otherwise, it's really annoying. So, and then we have also to limit the rocking of the structure, even to let's say not to well, we have some limitation provided by the manufacturer itself, so the inclination of the turbine should not oscillate too much. But we can do something on the rebars. As you see, the cage is impressive, it's huge, so not only is expensive because you need to use a lot of steel, but also it's expensive because you need high not educated, but let's say it's not easy to be built together, and you need experienced workers. Okay, so reducing the rebar may lead to a reduction in construction time and in material consumption. So there is a lot of space in reducing cost, and then increase the sustainability of this measurement. Okay, just for a comparison, you see that here, that's a person. So just so you can have a comparison between how huge and impressive this structure is. So what can we do in terms of rebar optimization? We can, let's say, first of all, we can understand if shear reinforcement is necessary, because, for example, in this case, Eurocodes ask for shear reinforcement, while American Institute is not. So the first question is, can we remove the shear reinforcement as Americans do, or we should keep it? Can we reduce the radial reinforcement? Okay, and can we see whether we can use fiber reinforced concrete to build our structure? Of course, we must consider both ultimate limit state and serviceability limit state. Okay, so for these reasons, we decided to go on considering 1G small scale test. Okay, well, they are small scale, but indeed they are still impressive because, of course, we started from a very large prototype at large scale. So considering a 19-meter diameter foundation, then our small scale was more about 1.3 meter of diameter. The length of the pile, representing the wind pile, was about 5 meters, and the whole testing structure was 8.5 meters. So still, let's say, an impacting structure. You can see here the small scale model. Here, that is the cage. Of course, everything is scaled, both in terms of bar diameters, aggregates, and so. Otherwise, we would lose some aspect in scaling procedure. And then we also need to design the soil itself, and especially the sand pool required to be representative and not to interact with the foundation itself. We decided to consider dry condition, and then we performed some numerical analysis just to understand how big this sand pool should be in order to avoid any interference. We were lucky enough because basically we are very far from the ultimate limit state capacity for vertical loading in this type of structure. So we can, let's say, consider a rather small sand pool, so only 3.5 meter diameter and 1.5 in height. I'm saying lucky because at the end of each test we had to remove the sand and put it back later on, and that operation was really tough. Well, so here you see the let's say the testing setup built. You see it's impressive. You have a reaction frame there with an hydraulic jack, which is simulating the action of the wind acting on top of the turbine itself. We had to add additional weight on the structure because of scaling purposes. Otherwise, we would lose, let's say, stress equivalency at the base. And then we put some displacements, transducers, and strain gauges inside the foundation itself, just to understand what was happening during the test. Okay, I'm saying we because we did it together with Luca and Bruno. It was an amazing trio. It was very well. It took when we were lucky, it was about 2 weeks of work to perform one test. We were never lucky, of course. So the campaign was set up in this way. So we have 3 different configurations with 2 repetitions for each test. The first one is the benchmark. So we went with the traditional reinforcement with Eurocode. So with shear reinforcement and let's say the amount of steel required by considering Eurocode. Then we consider another foundation without shear reinforcement, so with the same rebar, but without the one with, for shearing. And then the last one was, again, without shear reinforcement, but considering instead of the 50% of the radial reinforcement, which is the minimum one required by the Eurocode, we decided to swap it and consider using fibers instead, okay, just to see if we can, again, reduce the cost by reducing the time required to build all the cage, okay, so in situ. Considering test phases, we went for 3 phases mainly. Vertical load, simulating the installation of the tower itself. Cyclic loads, so we were trying to reproduce more or less the serviceability limit state. So we aimed at 60% of the ultimate limit state, and then we oscillate plus minus 20% of it. And then we tested the monotonic load, so ultimate limit state. We fixed the vertical loading, and then we went on by increasing the horizontal load as well as the momentum. So concerning the vertical test, basically we obtained, so we took advantage of the need to install additional mass to, let's say, simulate the construction stage step by step. Basically, we obtained a linear load displacement curve, so elastics. Okay, amazing. Okay, so it is, well, you see it's linear, and more or less the Young modulus was the one obtained by the bearing plating test. You see that here there is a small discrepancy in the measurement, but if you go into details and see, the discrepancy is about 1 or 2 sand diameters. So it's just a matter of having some grain which is there. Moving on the cyclic loading, so the serviceability limit state. Well, what we saw is that basically the structure was not was rigid, more not considering the strains on the rebars. Basically, it was always linear and not so stressed. While there is relevant, let's say, ratcheting induced inside the soil because of the interaction with the shallow foundation, both in terms of moment and rocking, that is the rotation of the base, and on settlements, increasing the number of cycles. Okay. In particular, if we look at rotation, this tends to stabilize soon, while the settlements is not so well. It's gonna stabilize, but it takes a higher number of cycles to get to the final value. That's an isostatic structure, so we are not very concerned about the vertical displacement, while rocking can be an issue. Well, when we move to ultimate limit state, then we clearly started seeing the interaction between the soil itself and the structure, which is, well, for a geotechnical point of view, it's amazing. And that's something which is, in general, disregarded by regulation and by traditional design. So there is room to go on with the research in this. And what we saw basically is that we were more or less elastic up to a certain value when some plasticity development started in the soil. And then you see this drop in the moment rotation curve associated to a large increase in strain measured on the rebars. So probably these were sign of crack opening in the foundation itself. So we have mainly 2 cracks opening, and indeed at the end of the test we end up seeing this by analyzing the structure. And more or less the response was almost ductile, even up to large rotation itself. So, well, the development of cracks seems to testify the, let's say, the development of a plastic hinge inside the foundation. So basically we concluded that this kind of failure, it's a mixed failure because of both soil approaching failure and the structure itself. Okay, this is, as I mentioned, disregarded in general, but it's not on the safe side. So that's why in geotechnical design we have so large factor of safety. Comparing the results from different foundations, we saw that more or less the response is similar. So we can conclude that shear reinforcement is not required, even by considering the measurement of the strain gauges applied on that bars. We saw that they were not solicited at all. And while for the fibers foundation, we see that we get slightly less maximum moment, which is weird, but can be explained even by considering the presence of cracks below the foundation. When you, well, I don't know if there is any expert of fibers for concrete here, but you know that in general this kind of concrete should not develop any cracks with it, because there is an homogeneity in the distribution of fibers inside the concrete, and this would prevent the crack formation. But at the end, when we cut the foundation itself, we found out that we had some fiber clots. So the foundation was not homogeneous. Okay, so that's why. And this is probably because of scaling procedure. So considering very small fibers, basically had this drawback, but all in all, the results was in line with all the other results. So concluding, we had some evidence in terms of serviceability limit state. So the foundation was not damaged by cycles, while we found out that there is a stable ratcheting in the soil. One may ask, how many cycles do I need before rotation are getting too large? So that's, let's say, that's a way in which we can evaluate the life of the structure itself. While considering the ultimate limit state, we have the results that the free solution are more or less equivalent, so we can reduce the rebars, so the cost may be reduced. With that, I would like to thank you all the research team involved in this experimental work, and also Enel Green Power, who founded this project. Thank you so much.
Thanks a lot. Pietro, we have one question already.
Yeah, well, a non-expert question, a layman. Do you consider also the tilting angle? Because you may have some rotation in the, and you know that in a wind turbine, you cannot have more than a certain little angle, otherwise it gets out of equilibrium.
Yeah, of course. We consider this, and we were inside the range suggested by the manufacturer. No, that's really important. As I mentioned, the rocking of the foundation should be limited. That's why we cannot reduce so much the dimension of the foundation. The geometry is fixed because if you reduce it, maybe you can still have room to, let's say, to apply load, but then you tilt too much, and then the wind turbine stops working. Yeah, that's a point. That's why we.
Thank you. It's okay.
Okay.
Other questions? No? Otherwise, Pietro.
Chiara, I have a comment from Martinelli. I was involved in the project, and I'm online.
Yes, please, go ahead.
Just a more comment on the fiber that Pietro mentioned. I think, sorry for the camera, I think the other camera was activated. No, just to mention that the fiber adopted in this project are, due to the strong scale adopted, it was 1/15, is not the optimum fiber that we have on the market. And this is justify also the comment of that Pietro did. And especially in if we move from a scaled specimen to the full scale, probably we expect a higher class for fiber reinforced concrete, with the fiber can have more potential in reality than what we have in this test. This is only my comment. So the fiber used due to the scaled specimen are not the optimum fiber, because the scale is 1/15, so we cannot use traditional hooked end fiber, but this is our straight fiber that are not the optimum one. In fact, the class, the material, the fiber reinforced concrete material was not the best one. So we expect that in full scale we can reach a higher result. This is only my comment.
Okay, thanks. So we can move on to the last, of course, but not least speaker, Marco Moscatelli, on the dynamics of cables with scatter elements, a metamaterial-like behavior. Thanks.
Good morning to everyone. Okay, so first of all, I want to thank the organizers for this seminar, for the very interesting topic they've chosen. My name is Marco Moscatelli, and I will talk about the dynamics of cables with periodic scatter elements for civil engineering application. I will be talking also about metamaterials, and I will try to show you how these two topics are connected to each other and how they are related somehow to energy transition. So this work was developed together with Claudia Comi and Jean-Jacques Marigot. So first of all, I just want to introduce a little bit the framework where we wanted to place ourselves. As you all know, energy transition means to study how we can move towards more sustainable energy sources. And energy harvesting can be a way to do this. For those of you who don't know what energy harvesting is a technology that aims to scavenge energy from ambient mechanical vibrations to provide remote sources of electrical power to recharge storage devices. Now, this technology can be sustainable in the sense that it exploits energy that are freely available around us, which are ambient vibrations. And in particular, in our case, we were interested to apply this technology for structural health monitoring applications, where basically one needs typically a lot of sensors that need electrical energy to work. And actually, this is interesting because there was before a question after the second presentation that was exactly about how to give energy to sensors to measure, to make some remote measurements. So this can be probably a way, and I hope that this can contribute also to that. Basically, what is a structural health monitoring? Is the characterization of the progressive decay of structural performances. And this is done typically to optimize the maintenance, the maintenance and the safety of a structure. In our case, we were interested in the monitoring of long-span structures characterized by the presence of cable systems with periodically distributed scatter elements. And of course, the most obvious application of these systems is in suspension bridges, but all other applications can also be found in overhead lines and cableways as well. Where are the advantages of energy harvesting for structural monitoring? First of all, we can avoid complex wiring systems. We can reduce the use of chemical batteries, and connected to these two considerations, we can also decrease the costs. So we can decrease, for instance, the cost in of the replacement of the chemical batteries. And the message of this presentation is that we would like to enable the energy transitions by enhancing the energy harvesting for improving structural health monitoring. Now, the reason why we chose these specific systems is the fact that they have a common denominator, which is periodicity. So the keyword here is periodicity. Why? Because it is well known that periodicity in dynamics can be strongly beneficial in wave propagation problems. Typically, this property is exploited to develop materials that are able to attenuate propagating waves. These are known as metamaterials. So metamaterials basically are artificial composite materials characterized by periodic repetition of a unit cell in space, and where the attenuating capabilities come from the periodic microstructure of the system. So basically, a wave that is trying to propagate through the metamaterial can be attenuated by the metamaterial itself. And in this presentation, I will talk about periodic cables, and I will try to show you how they can behave as periodic metamaterials with attenuated capabilities. Then we'll discuss on how these periodic cables can be, and this periodicity property can be exploited to optimize the harvesting of mechanical energy. So why do we need to optimize this technology? Because the functioning of energy harvesters is typically localized in space, while sources of vibrations, so sources of our energy, are distributed in space. And so there is a need to convey the energy towards the harvester. And for this, we found interesting to exploit what we knew from the metamaterials world. That is, a defect of periodicity inserted in the metamaterial can behave like a cavity where the mechanical energy can be trapped and focused. So in our case, with our periodic cable, we can, in principle, insert a defect of periodicity, place our energy harvester inside that defect, and the behavior of the energy harvester could be enhanced by the fact that the system localizes its motion around the central defect, the defect. So now let me show you some results. First of all, we start off with periodic cables. So here we need some assumptions in order to theoretically treat and model the problem. The assumptions are listed in the slide. So we are dealing with a perfectly flexible and inextensible one-dimensional body, that is our cable. We are considering a number n of point-wise masses that are periodically distributed along the cable. Now these masses can represent, for instance, masses that are directly attached to the cable. They can also represent masses that are hanging to the cable by means of elastic springs. They can also represent elastic supports. The equations governing the motion of our system are the ones listed in the slide. So we have the equation of motion, which is the first one. Then the second one is the inextensibility condition. And then finally, we have some jump conditions at the locations where we have a mass. Now, this system of equations is a highly nonlinear system. But with our assumptions, we can demonstrate that this system actually reduces to a system of discrete linear equations that have the form that have the same. Basically, that is the relation written in this slide, where we have U2, which is the displacement, the vertical displacement of the cable. Then we have delta I, which is a discrete Laplacian operator. And we have this mu, which can be interpreted as an equivalent mass that depends on the frequency omega. So omega for us is the frequency. In order to find a solution to the problem, we need to solve the system of equations, the system of discrete linear equations, and solutions actually depend on the behavior of this equivalent mass. For instance, here in the slide, I'm reporting the behavior of this equivalent mass when the masses are directly attached to the cable. And what we can find is that whenever this equivalent mass is either greater than 4 or smaller than 0, then waves cannot propagate freely along the cable. They are attenuated. So what we find basically are the so-called band gaps, which are intervals of frequencies where waves are attenuated. And this is a typical behavior of a metamaterial. So this is a first result. And in this slide, the band gaps are the colored region in this case. So this is the propagation problem. Now let's see what happens if we consider boundary conditions. When we consider boundary conditions, the problem is actually an eigenvalue problem. And so the solutions are eigenvalues, which are the asterisks in the plot. So here we have a second result, which is the fact that these asterisks only appear in the passbands, so outside our band gaps. And you can see it also in the plot because the asterisks are only present outside the colored regions. Now, with these two results in mind, we can, so band gaps and the fact that eigenvalues appear only outside the band gaps, we can analyze the periodic cable with a defect. And for us, the defect will be, well, we'll remove the central mass from our periodic system. So let us again consider the spectrum of the eigenvalue problem, this time of a system with a defect. Again, we have the band gaps, which are given by the colored regions, and we have the asterisks, which are the eigenvalues, so the solutions of our eigenvalue problem. Again, we can see that we have some asterisks that appear only in the passbands, so outside the band gaps, but this time, due to the presence of the defect, we have also eigenvalues that appear inside our band gaps. And if we consider the modes corresponding to these specific eigenvalues, what we see is that the cable oscillates around with a motion that is focused, concentrated around the central defect. So here, for instance, in the slide, you have on your right the motion of the cable. You have the first defect mode corresponding to the first eigenvalue inside the first band gap. And as you can see, the motion of the cable is localized mainly around the central defect. So we had these, in my opinion, nice results, nice theoretical results, and we wanted to check their validity also experimentally. So for this, we used the system that is depicted in the slide. You have basically a metallic cable in tension between a fixed support on the left and a shaker on the right. We imposed a motion with the shaker, and we measured the vibrations, the oscillations of a cable around its equilibrium configuration by using some optical sensors. So for instance, in this case, we used 5 sensors along the cable and 1 sensor above the shaker to measure the input signal. Now, let's consider the case without the defect, so the periodic system. Here we are, in the plot, we are comparing the theoretical results with the experimental results. The theoretical results are given in terms of band gaps, which are, again, the colored regions, while the experimental results are given in terms of Fourier transform of the signals that are measured by 3 sensors. In particular, you have the black curve, which is the Fourier transform of the signal measured by, of the input signal, basically. You have the orange curve, which is the Fourier transform of the sensor 1, and the violet curve is the Fourier transform of the sensor 3, which is farther from the input. Here, this curve, when you have a peak in these Fourier transforms, it means that we are activating a mode of our system. And so by looking at this graph, we can directly see that the peaks indeed respect our theoretical findings. Indeed, they are disposed only in 2 bands around our first band gap. So with this, we validate the first 2 results, so the band gap, the presence of band gaps, and the fact that eigenvalues only appear outside band gaps. Now let us consider the case with a defect. So we remove the central mass from our system, and we made the same measurements as before. Again, in terms of spectrum, we compare the theoretical results in terms of band gaps with the Fourier transforms. and which are the experimental results. And now you see that the behavior is different. Indeed, most of the peaks are still placed outside the first band gap, but now we have a peak that appears inside the band gap, and this peak should correspond to our first effect mode. And to check this, we can plot the displacement that is measured by our 5 sensors. So here you have the black circles, which are the locations where we have a sensor. And we connected the known displacements at these locations with, sorry. Okay. We connected these locations with lines to display the motion of our experimental mode. And you can already see that this motion is localized around the central defect. Moreover, we can compare this experimental mode with the theoretical one that I was showing you before. And as you can see, there is a good comparison between the two, meaning that the peak we were looking at before, the peak inside the first band gap, indeed corresponds to our first defect mode. So with this, I've concluded, just have some final remarks. Our theoretical demonstration of the presence of band gaps can be helpful to predict the model response of systems of this kind. Moreover, we have shown that the localization can be exploited for enhancing the energy harvesting technologies. And in particular, our theoretical approach allows for an easy detection of the defect modes. And we think that this can open up the possibility for more sustainable structural health monitoring. So with this, I've concluded, and I thank you for your attention.
Many thanks, Marco, for the presentation. Do we have questions? Not. Probably everyone is very tired. Thanks again for the presentation and to all presenters. And now I leave the word to Paola for the last just few words in order to thank, first of all, our conveners, Chiara Corbari and Massimiliano Cremonesi, for their commitment with the organization of the event, as well as Davide Marzi for his help in the technical issues for the seminar. Of course, special thanks to our guests, even if they are no longer here. I think we should appreciate their contribution. They shared with us their knowledge, their expertise on such key topic like energy transition. But above all, many thanks to all our speakers, our internal speakers, I mean, for sharing your expertise, your research and innovation activities. In my opinion, today you gave us a really broad overview on technologies of civil and environmental engineering, technologies on which our department is deeply engaged and that are for sure of paramount relevance in all issues involved in energy transition. So many thanks to you. As you know, within the context of this event, our department has promoted an award recognizing outstanding contribution delivered by our young researchers. In my opinion, all of you did a great job and ensuing excellent quality presentation. All video recordings will be shared on our website as soon as possible, I think.
Okay, and among them we are going to, or better, the scientific committee is going to award 2 of them as winner for the Young Researcher Prize. We are going to let you know as soon as possible who the winner are. Thank you all for attending the seminar till its end, and I hope you would have learned as much as I learned today. Thank you so much, and I hope to see you to our next event in autumn.